Hello everyone, my name is John. In this video, I'll be teaching you how to make a third-person grinding system in Unreal Engine 5 using C++. You'll learn how to build your own custom character movement component, a feature that is only possible with C++. We'll be implementing our own grinding movement mode and write code that will handle all of the movement. I'll also show you how to create grindable platforms, which are static mesh actors that contain one or more spline components. These splines will define the paths that your character will follow while grinding, and you'll be able to easily add or remove them directly in the editor. We'll also go over essential 3D math topics, including how to use quaternions to smoothly rotate your character from one orientation to another. Finally, we'll go over how to add grinding effects, which includes adding spark particles underneath the character's feet, and sound effects that follow the character. If any of this sounds interesting, please stick around. Before we get started, there are a few things I'd like to mention. First, I would like to mention that closed captions are available. Please turn on the English option if you need captions. Please don't turn on auto-generated captions, as they won't be 100% accurate. I have a disability which makes it difficult for me to speak clearly, so I'd recommend turning on captions in order to fully understand what I'm saying. The last thing I want to mention is all of the source code for this project is available in a GitHub repository, just in case you need it while following this tutorial. The link to the repository is in the description. Alright, let's get started. For this tutorial, we'll be using the third-person template. This way we can skip building a character from scratch. Let's select the third-person template and choose the C++ option. I'm going to name this project Grinding Tutorial, but you can of course name this whatever you want. Let's click the Create button. What I'm going to do now is close the project, open up the Visual Studio solution, and launch the program with the debugger. You can choose to launch the program without the debugger, but it's a really helpful tool. The first thing we're going to do is implement a class called Grinding Platform. This class will allow us to create objects that our character could grind on. It will be derived from the static mesh actor class and will contain spline components. These spline components will represent the paths that the character will follow while grinding. In the editor, we'll be able to easily add spline components to a grinding platform. When our character jumps and lands on a grinding platform, our code will determine which spline component will be the best path for our character to follow. This is the primary goal for this grinding platform class. Let's implement this. Let's create a new C++ class. This class will be derived from the static mesh actor class. And let's name it Grinding Platform. This class is going to contain spline components, so let's forward declare the useSpline component class in the header file. Our grinding platform class needs to be able to manage multiple spline components, so we need some kind of data structure to store all the spline components that will be managed. We'll be using the T-array data structure to store the spline components. If you're not familiar with what a T-array is, it's Unreal Engine's own implementation of a dynamic array. It's similar to the vector data structure from the standard template library. So let's define a T-array of pointers to spline components. Let's call it grind splines. Please let me know in the comments if you want me to explain what a T-object pointer is. Let's mark this as a U property. We need to make this edit instance only, so it'll be editable only when an instance of a grinding platform is placed in the level. Let's compile and run this. Next, we need to create a blueprint class based on the grinding platform class we wrote in C++. Head over to the C++ classes folder and locate the grinding platform class. Right-click on it and choose Create Blueprint class based on grinding platform. We'll name this new blueprint class BP_grinding platform. To keep things organized, let's create a new folder called Grinding and move our newly created blueprint class into it. Now go ahead and open up BP_grinding platform. For the default static mesh, I'm going to set it to the cube static mesh, but this is totally up to you. I'll also be changing the material. Let's close this. I'm going to delete this circular platform. Go ahead and place an instance of the class into the level. We do this by dragging the blueprint class into the level. I'm going to scale it so it looks like a nice platform for grinding. Alright, let's move our mouse over to the details panel and search for grind splines. Here is the grind splines T array we defined in C++. Let's try to add a spline component to this array. When we add a new spline component to the array, the element is set as none. This is the same as null. This is a problem because we don't want our elements to be null. When we click on that plus icon, we want a new instance of a spline component to be created. Let's update our C++ code to handle this. Let's first empty out this array, then open up our C++ code. Alright, so we need to find a way to detect when somebody is attempting to add to the grind splines array in the editor. We need to be notified when the user presses that plus icon. Luckily, there is a function that is called whenever a property is changed in the details panel. That function is called post_edit_change_property. So let's override that function. Also, we need to make sure that this function is only compiled in editor builds. This function shouldn't be included in our shipping builds because it shouldn't exist outside of the level editing process. Let's use the with_editor macro to ensure that this function only compiles in our editor builds. Let's define this function. Once again, let's use the with_editor macro to ensure that this only gets compiled in editor builds. First, we need to call the parent version of this function so it doesn't lose any base functionality. Okay, so how do we determine if the user attempted to add a spline component to the grind splines array? This property changed event parameter could give us a hint to what exactly happened to this object in the editor. The property changed event parameter has a property called change type that tells us what was changed. Let's take a look at this. Here you can see that there's an enumerator called array_add. When a new element is added to the array in the editor, change type will be set to array_add. Okay, so let's check if the change type property is equal to array_add. So when the user tries to add a spline component to the grind splines array, this case will be executed. Okay, so what should we do when the user tries to add to the array? When the user tries to add to the array, that new element will be set as null. We don't want it to be null. We want it to point to a new instance of a spline component. We should replace that null element with a new instance of a spline component. Let's first find the index of the null element. We can do this with the find function. Now let's check if the element was found. We can do this by checking if the index is not equal to the macro index underscore none. Our next step is to create a new instance of a spline component, and once we've done that, we should attach it to the root component of this grinding platform. We can do this by calling the add component by class function. This function allows us to dynamically create an actor component and will automatically attach it to the root component of this object. Oh, don't forget to include the header file for the spline component class. For the first parameter, it needs the class of the component that we're creating. Let's pass in the U class for the spline component class. The next parameter is a boolean called bManualAttachment, which indicates if we want to manually attach this component to our object. Let's pass in false. The next parameter needs the relative transform to the parent. Let's just pass in an empty f transform. The final parameter is a boolean called bDeferredFinished, which indicates if we want to delay the creation and registration of this component. Let's pass in false. We need to cast the return value from an actor component to a spline component. To be safe, let's check if the creation of the spline component was successful. It should be successful, but let's be safe. We also need to call a function called addInstanceComponent to properly see our new spline component in the editor. One thing I want to mention is when we're using spline components, we shouldn't be allowed to scale it. When we scale the spline component in the editor, the distance of the spline becomes inaccurate. For this reason, let's lock its scale. Let's first set its scale to a uniform 1.0. Now let's call a function named setAbsolute. For the first parameter, let's pass in false because we're not concerned about its location. For the next parameter, let's pass in false because we're not concerned about its rotation. For the final parameter, let's pass in true because we want to lock the scale. So what this function did is prevent the spline component from scaling when we scale the parent grinding platform. Now finally, let's assign our new spline component to the element that was previously null. This way the element is no longer null and is now pointing to our newly created spline component. Let's compile and run this. Let's select our grinding platform and add new spline components to the grind splines array. As you can see, a new entry was added to the array. We need to click on the grinding platform one more time to see the changes fully take effect. So if you don't see the splines show up in the editor, try clicking on the grinding platform one more time. As you can see here, the spline component was properly attached to the grinding platform. We can move it around, increase the distance, and so on. Let's try adding more. You can see here that we can add as many as we want. Okay, so now that we've handled adding elements, let's handle the case where the user presses this reset button. When the user presses this button, it resets the element to none. Also, the spline component still exists and is still attached to the grinding platform, so the spline component wasn't properly destroyed. So let's find a way to properly get rid of the spline component when the reset button is pressed. Let's empty out the array. Now head on over to our C++ code and we'll handle this reset case. Alright, so how could we check if the user pressed the reset button? Something that can help us figure this out is a property called ownComponent. Let's take a look at the actor class definition. I'm in the actor.h file in the game framework folder. Let's take a look at the property called ownComponent. This ownComponents property is a t-set that contains all of the actor components that is owned by an actor. So whenever we create and attach a spline component to a grinding platform, it gets added to this ownComponent set. Whenever the user clicks on the reset button, the element gets set to null, but the spline component still exists in the ownComponent set. So what we can do is compare the spline components in this set with the spline components in our grind splines array. If a spline component exists in the ownComponent set, but not in the grind splines array, we should destroy the spline component, then remove all the null elements from the grind splines array. Let's head back to our grindingplatform.cpp file and start coding this logic. The first thing we need to do is extract all of the spline components that are in the ownComponent set. To do this, we'll create a t-array to store the spline components. Let's call it spline comps and ownComps. Next, we need to fill this array with the spline components that belong to the grinding platform. We can do this easily by calling the getComponents function and passing in our array. Now the array contains all the spline components attached to the grinding platform. Now we need to iterate through this array and check for any spline components that aren't in the grind splines array. Let's use a range-based for loop to accomplish this. For each spline component, if it doesn't exist in grind splines, we'll destroy it by calling destroyComponent. Finally, we need to remove all the null elements from the grind splines array. We can do this with the removeAll function and pass in a predicate that tells it which elements to remove. I'll go ahead and write out the code first, and then I'll explain how it works. Okay, let me explain how this works. We want to remove all the null elements from the grind splines array. We can do this by calling the removeAll function on the array, and what this function does is iterates through the array and removes all the elements that match a predicate. For the predicate, we pass in a lambda where the parameter is a spline component. This lambda returns true if the element is null. So essentially, this lambda is telling the function to remove all of the elements that are null. That's pretty much all of the code we need to write to handle the case when the user presses the reset button. If you want, you can refactor this code and put it in a function. I honestly don't think it's necessary, because this code should only be executed within the context of this posetChange property function. If we put this code in a function, it's only going to be called in one place, and it's never going to be called again. You also need to remember to use the with_editor macro to ensure it only gets compiled in editor builds. For those reasons, I don't think it's beneficial to write a function for this code. What I would recommend doing is placing this code in its own scope. This way it sort of resembles a function definition without the drawbacks of defining and calling functions. We can also write a comment above it that explains the goal of the code. Let's also write a comment for this case. Before we continue, there's one thing I'd like to address, and it has to do with the performance and efficiency of this code. This code can be seen as inefficient because we're creating arrays and iterating through data structures multiple times. It is inefficient, but I think it's perfectly fine in this context. First of all, this code is only executed in editor builds. It's not going to be compiled in shipping builds. It's also not gameplay code. On top of that, it's only executed when we edit a property on a grinding platform, and the grinding platform isn't going to have hundreds of components to iterate through. This is why I think this code is completely valid with regards to efficiency. Alright, I know some of you are yelling at your screens telling me to shut up and move on already. I'm sorry. Let's compile and run this. Oh, I forgot to delete this spline component the last time we had the editor open. Let's delete it before we test our code. Okay, so let's add a spline component to this grinding platform. Now let's see what happens when we press the reset button. Great, our code works. When we click on the reset button, the element gets properly destroyed. It's removed from the grind splines array and is no longer attached to the grinding platform. Alright, so what's next? There are still a few more cases we need to handle when editing a grinding platform. For example, what happens when you try to duplicate a spline component in the level? Let's test this out. First, let's create a new spline component and place it on the edge of the grinding platform. Let's also extend the length by selecting the last spline point and dragging it out in this direction. Now let's duplicate this spline component. Select the spline component again, then hold the Alt key and drag it to the other side of the platform. Now we've got two spline components. Here's the problem we need to fix. That new spline component we just created wasn't automatically added to our grind splines array. We need to write some code that ensures that any spline components that are created in the level get added to the grind splines array. Let's go back to our C++ code. Now, in order to detect if a new spline component was created in the level, we won't be using the poseditChange property function. The reason why is because this function is only called when we edit a property in the details panel. This function won't be called when we duplicate a spline component in the level. We need to take advantage of another function called onConstruction. Let's override that function. Head over to the grinding platform's header file. Let's override the onConstruction function. Let's move the function definition above this preprocessor condition, because this function should be compiled regardless if it's an editor build or not. Okay, so what is the purpose of this onConstruction function? The onConstruction function gets called whenever an actor is spawned, or whenever a property is changed on an actor. This is especially helpful for us because this function will be called whenever a new spline component is created in the level. Alright, so here's our goal. Whenever a new spline component is created in the level, we need to check if it was already added to our grind splines array. If it wasn't, we need to add it to the grind splines array. Let's do this by iterating through all of the actor components that the grinding platform owns. We get the set that contains all of the actor components by calling the getComponents function. Next, we need to check if the current actor component is a spline component. Let's do this by casting it to a spline component. We now need to check if the cast was successful and if the grind splines array doesn't contain the spline component. If it doesn't contain the spline component, we need to add it to the array. Let's compile and run this. Let's select this grinding platform again and delete one of the splines from the grind splines array. Let's select this spline component. Now I'm going to duplicate it by holding the Alt key and dragging it. I'm going to drag it to the other side of the platform. Now let's check the grind splines array to see if the new spline component was successfully added to the array. Now the grind splines array has 2 spline components. Awesome, we got it to work. There's one more case we need to handle when editing a grinding platform. What happens when we try to delete a spline component outside of the grind splines array? For example, what happens when I go to the component hierarchy and delete it from here? It's removed from the component hierarchy. The grinding platform no longer owns the deleted spline components. However, those deleted spline components are still being pointed to in the grind splines array. These deleted spline components should also be deleted from the grind splines array. Let's go back to our code and handle this problem. Let's close this, but don't save it. This case should be handled in the onConstruction function, because whenever a component is deleted from the component hierarchy, the onConstruction function gets called. PostEditChangedProperty does not get called. What we should do is iterate through all of the splines in the grind splines array and search for the splines that are in the array, but not in the set of own components. So if a spline exists in the grind splines array, but not in the own component set, we need to remove it from the array. This can be done with the removeAll function. This should look familiar to you since we've used this method before for the element reset case. So what this does is remove all of the splines that are not null and if they don't exist in the own component set. We could call this ownComponent function to check if the spline exists in the set of owned components. Okay, so that's all of the code we need to write to handle this case. Before we test this out, let's add this code on top of the onConstruction function. Whenever a property is changed in the editor, the onConstruction function gets called before the postEditChangeProperty function gets called. Whenever there's a null element in the grind splines array, we should pass off the responsibility to the postEditChangeProperty function. This code prevents things from going wrong when we reset an element, because that case should be handled by the postEditChangeProperty function. Let's compile and run this. Let's test this out by deleting the spline components from the component hierarchy. Let's check the grind splines array to confirm that they were properly removed. As expected, the array is now empty, which is exactly what we want. Perfect. Now let's add 4 new spline components and place them along each edge of the grinding platform. This setup will allow our character to grind along the edges once we implement that functionality. Just follow along with me. Let's add a new spline component. Let's select the spline component. I'm going to switch the view from perspective to the top orthographic view. Let's switch the view mode from wireframe to lit so we can clearly see our grinding platform. Let's move the spline to the top right corner. Now we're going to select the second spline point and stretch it to the other corner by dragging it. Now let's select something else, then select the spline component again. We're going to duplicate it by holding the Alt key and drag it to the other side. Now we have 2 spline components. Next, we're going to duplicate this spline component and rotate the duplicate by 90 degrees. So let's hold the Alt key and rotate the duplicate by -90 degrees about this axis. Let's shrink the spline component by selecting the second spline point and dragging it in this direction so it touches the other corner. Let's select something else, then select the last spline component that we made. Now we're going to duplicate the spline component and bring it to the other side by holding the Alt key and dragging it. The spline components look a little too low, so let's select every spline component and raise it higher so it's right above the platform. And there we have it. Here are the 4 spline components that will be used when our character grinds on this platform. Let's take a break from the grinding platform class for now and shift our focus to character movement. We need to come up with a way to detect if the character is right above a grinding platform. At that point, the character should begin grinding on the platform that they've come in contact with. To support this, we'll also set up a dedicated movement mode for grinding. The best approach for handling all of this is to create a custom character movement component that takes care of all the grinding logic. So let's create our own custom character movement component class that our third-person character will use. Let's create a new class that is derived from the character movement component class. This is actually one of the many advantages that C++ has over Blueprints. With C++, you're able to create your own class that extends the functionality of the base character movement component class. This can't be done in Blueprints. You're not able to create a Blueprint class that extends the character movement component. I'm going to name this class Custom Character Movement Component, but you can of course name this whatever you want. Our next step is to update our third-person character class so it uses our custom character movement component class and not the base character movement component class. Let's navigate to the class for our third-person character. For my project, the class is called Grinding Tutorial Character. It might be named differently depending on how you named your project. Let's modify this constructor here so it uses a different constructor that has an fObject initializer for a parameter. Let's head over to the class's CPP file and update the constructor's definition. This fObject initializer parameter allows us to override components in a parent class. What we need to do is override a property called character movement component name. This property is defined in the parent aCharacter class and is used to choose the character movement component. We need to override this so it uses our new custom character movement component class. To do this, we're going to call the parent constructor, pass in the object initializer parameter. On that parameter, we're going to call a function called setDefaultSubObjectClass. This is where we're going to override the character movement component name. Let's pass in our custom character movement component class for the template argument. Then pass in character movement component name, since that's what we're overriding. And of course, don't forget to include the header file for a custom character movement component. Let's compile and run this. Let's open our Blueprint class for our third-person character and verify that the third-person character is using our custom character movement component. You can see here that our third-person character is now using our new custom character movement component. If your Blueprint class is still not using your new custom character movement component class, then it's most likely because you're using an older version of Unreal Engine. There was an issue in older versions of Unreal Engine where Blueprint classes wouldn't reflect changes made in C++. I'm using version 5.6 which fixes this issue, but if you're experiencing this problem, a hacky way to fix this is by changing any property in the blueprint, pressing compile, then just reset it to the original value. You'll then see the blueprint use the new custom character movement component class. If you're still having issues, just leave a comment and I'll help you out. Alright, our next goal is to figure out how to detect when the character is directly above a grinding platform so they can start grinding. The first question we need to ask is, when should the character even be looking for a grindable platform? What state should they be in before transitioning into a grind? The answer is when the character is falling. When the character is falling, they should actively check for nearby grinding platforms every frame. We're going to be taking advantage of our character movement component because it will give us the relevant information we need to solve this problem. Let's jump back into the code. I'm in the header file for our custom character movement component. Before we start adding logic, let's take a quick look at the base class called character movement component. I'm now in the file called character movement component.h. Let's take a look at the movement update functions. This class has several functions that handle movement logic for the different movement modes. There's one for walking, swimming, flying, and so on. The one that we're interested in is phys falling. This function is called every frame while the character is in the falling movement mode. What we're going to do is override phys falling in our custom character movement component so we can add our own logic to detect grinding platforms while the character is falling. Let's go ahead and set this up. Head back to the header file for our custom character movement component and override the phys falling function. Here's the function signature. Make sure to call the parent version of this function so we keep all of the base functionality. Next, we'll create a helper function to handle grind detection. Let's call it try enter grind. This function will return a boolean indicating whether the character successfully found a grinding platform and entered a grind. Back in phys falling, we'll call try enter grind and store its return value in a boolean variable, which we'll name be entered grind. Now let's head back to the definition of try enter grind. The first thing this function needs to do is check if the character is directly above a grinding platform. A good way to handle this is with the sphere trace. Let me explain how this is done. Once the character starts falling, we'll generate a sphere just below their feet every frame. If that sphere collides with something, we'll get information about the hit. The collision information is stored in a struct called a hit result. From there, we can check what type of object the sphere collided with. If the object is a grinding platform, the character should immediately transition into a grind. In the try enter grind function, let's actually prevent this function from continuing if certain conditions aren't met. This first condition checks if the current movement mode is the falling movement mode. If it's not, the function should immediately exit and return false. The second condition is that the velocity z component should be a negative value. The reason why is because the character should be falling downwards. If the z component is a positive value, that means the character is falling upwards, which we don't want. Our next step is to generate the sphere trace that will handle detecting grinding platforms. To do this, we'll call getWorld. And on the return uWorld object, we'll use the function sweep signal by channel. This function lets us sweep a shape through the world and check for collisions along the way. The trace works with something called a collision channel, which is basically a way of filtering what the trace interacts with. For example, say we're performing a line trace in the world, and that trace uses the visibility collision channel. Any object in the world can decide how to respond to that channel. It can decide to block it, overlap it, or ignore it entirely. These responses are configured through the object's collision profile. For grind detection, we'll create our own custom collision channel and profile specifically for identifying grinding platforms. I'll also leave a link in the description to a great article on collision filtering in Unreal Engine if you want to learn more. So in our case, we'll be calling sweep signal by channel since we're tracing with the collision channel, and only need to check against a single object. For the first parameter, it needs a hit result. Let's define a hit result and pass it in. This will give us information about the collision, if any occurred. For the next parameter, it needs a vector that represents the starting location of the trace. Since we're using a sphere, this is basically where we want the sphere to be located. Remember, the sphere should be located right below the character's feet. Let's create a vector called traceStart, which will be the starting location for our trace. We want the location of the trace to start underneath the character's feet, so we can simply call the getActorFeet location function to get that location. Let's pass in traceStart to the function call. For the next parameter, it needs the end location for our trace. Our trace doesn't need to sweep across multiple locations. We would need an end location if we want the sphere to kind of stretch from one location to another. But we won't need to do that. We just need to generate a single sphere and check if an object blocks it. For that reason, you would think that we could just pass in traceStart for this argument, but doing so could cause certain objects to be ignored. I honestly don't know why that happens, so what we should do is add some offset to the end location. The offset doesn't need to be large. I'm just going to add the direction vector that points downwards. Let's pass it in. For the next parameter, we need to provide a quaternion that defines the rotation of the sweep. Since we're using a sphere, the rotation is irrelevant. No matter how you rotate a sphere, you'll get the same sphere. That means the rotation we pass in doesn't actually matter. When rotation is irrelevant, we pass in the identity quaternion, which simply represents no rotation. For the next parameter, it needs the collision channel that we'll be using for this trace. We're going to define our own custom collision channel specifically for searching for grinding platforms. To do that, we need to first launch the editor. Let's comment this out and add this return statement here so our compiler doesn't yell at us. It'll just be placeholder code for now. Let's compile and run this. Let's navigate to the project settings. Let's head to the collision settings. Now here is where we define our own custom collision channels. Click on this new trace channel button. I'm going to name this channel grind. For the default response, I'm going to set it to ignore. Now click accept. There's our new collision channel. What we need to do now is create something called a collision profile. Collision profiles allow us to configure how certain objects respond to different types of collisions. We need to make a collision profile for our grinding platform so it's able to respond to our grind collision channel. Open up this preset drop-down menu. Click on new. Let's name this grinding platform. For this collision enabled setting, we're going to set it as collision enabled query and physics. For the object type, I'm going to leave it as world static. I'll just add this description here. Now for the collision responses, I want it to block everything. We especially need it to block our grind collision channel. So when our sphere trace collides with an object that uses this profile, it will block it as a response. Click accept. Let's close this and go back to our code. Alright, so our next step is to make sure that our grinding platform class uses the new collision profile we defined. So we need to write some code that sets the collision profile for the grinding platform class. Let's head over to the header file for the grinding platform class. We should set its collision profile in the constructor, so let's define a constructor for this class. Now here in the constructor, let's call the getStaticMesh component function. The static mesh is the component that handles collision. Now on the return static mesh component, let's call the setCollisionProfileName function. For the parameter, it needs the fname for the name of the collision profile we'll be setting it to. If you remember, the name of the collision profile was called grinding platform, so let's pass in an fname with the grinding platform name. To be safe, let's check if this is a null before executing this code. It shouldn't be null at this point, but let's be safe. Let's head back to the try and to grind function in the custom character movement component.cpp file. Let's uncomment this. So for the next parameter, it needs the collision channel we'll be using. This uses the eCollision channel enum. Let's actually take a look at the eCollision channel definition. As you can see here, there are several different enumerators for the different collision channels. But which one of these enumerators corresponds to our grind collision channel? There isn't an ECC_grind anywhere. So the way we find out which enumerator to use is by looking at the engine's config file. So you're going to want to look for a file called defaultengine.ini. So open up the directory for your project, go to the config folder. You'll then see the file right here called defaultengine.ini. I'm going to open it with Notepad. Let's search for the name of the collision channel. In our case, it's called grind. As you can see here, here's the information associated with our grind channel. And right here, it tells you that the enumerator that this channel uses is called ECC_GameTraceChannel2. Let's pass that into the function call. Better yet, let's define a variable that better documents that we're using the collision channel specific to grinding. Let's pass it in. For the next parameter, it needs the collision shape for the trace. We'll be using a sphere, so what we can do is call a static function from the fCollisionShape struct called makeSphere. The parameter for this function call needs the radius of the sphere. A good idea would be to define a member variable that stores the length of the sphere's radius. Let's do that. So head over to the header file for this class. Let's define a float member variable called grindDetectionRadius. For the default value, I'm going to set it to 50. I'm going to mark it as a uProperty, so you have the option to edit this value in the Blueprint class. Let me know if you have any questions about these uProperty specifiers. Let's pass it in. There's one more parameter for this function, and it's the collision query parameters, but it's optional and we won't need it for our case. Alright, so let's write some code that tests this out. We can use the bBlockingHit property on the hit result to check if there was a collision. Let's return false if there wasn't a collision, because that means the attempt to search for a grind was unsuccessful. If the sphere trace collided with the grinding platform, let's just print a message out to the screen for now. The message is going to say hit grinding platform. I'm also going to add some debug code that will help us visualize our trace. We can use the drawDebugSphere function to draw our sphere when we're playing the game. For the first parameter, it needs the uWorld object. Let's call getWorld. For the next parameter, it needs the location of the center of our sphere. Let's pass in traceStart. The next parameter is the radius. Let's pass in grind detection radius. For the next parameter, it needs the number of segments, which is the number of lines used to draw the sphere. I'm going to pass in 32. The next parameter is the color of the sphere. I'm going to use red. This function has additional optional parameters, but we'll just skip them. Oh, I made a mistake. This code should be placed right before this return statement, so we can still see the sphere even when there's no collision. Alright, let's compile and run this. Okay, so I'm going to make my character jump. As you can see, when the character is falling downwards, our sphere trace is generated. Now I'm going to attempt to jump and land on the grinding platform. Here you can see that when the sphere collides with the grinding platform, our message gets printed out to the screen on the top left. This demonstrates that our code is working correctly. Awesome job. Now that we've found a grinding platform that the character can potentially grind on, we should write some code that determines if the character is able to start grinding on the grinding platform. There are a few instances of when the character shouldn't start grinding. For example, if the character lands on a grinding platform and the character is too far away from any of the splines, the character shouldn't begin to grind. So what our code should do now is iterate through all of the splines on the grinding platform. It should select the best fit spline component that the character should grind along based on distance. If it found the best fit spline, the character should start grinding along the spline, else it should ignore the grinding platform. Let's head to our grindingplatform.h file, and what we should do is define a function that returns the array that contains all of the spline components. Let's call this function getGrindSplines. It's going to return a const L value reference to an array of spline components. It should be const because the caller shouldn't be able to modify the array. Let's return our GrindSplines array. Now head over to the custom character movement component, and let's write a range-based for loop that will iterate through all of the spline components on the grinding platform that the character just landed on. We're going to use the function we just defined to get the spline components. Don't forget to include the header file for spline components. Now, for each of the splines on the grinding platform, let's find the location on the spline that is the closest to the character's location. We can get this location by calling a function on the spline called findLocation closest to world location. This function allows you to pass in a location, and it will return the location on the spline closest to the location that you passed in. This is done in world space. We actually won't be using this function. Sorry for lying to you. We're going to be using a function called findTransform closest to world location. This function will return a transform instead of a location. If you don't know what an f-transform is, it's a struct that contains rotation, location, and scale. Well, location/translation. We'll be needing the rotation, and don't worry, later on I'll explain why. For the first parameter, it needs the location that we want to find the closest spline location to. We need to pass in the character's location. Let's actually define a variable that stores the character's location. We're going to use this value multiple times. The next parameter needs an enumerator from the eSpline coordinate space enum. We want the return transform to be in world space, so let's pass in world. Let me know in the comments if you have any questions about this. Let's store the return transform in the variable and name it grindTransform. It's been a while since we tested our code, so let's add some debug code to test if we were able to get the closest location on each spline. I'm just going to copy and paste this draw debug sphere code. And let's replace trace start with the location in the grindTransform. We can get the location by calling getLocation. Alright, let's compile and run this. I'm going to enter a console command that will allow us to see splines while playing our game. Let's press the tilde key to open the console and type in show splines. It might be difficult to see in the video, but the splines are now visible. Okay, so now I'm going to jump and land on the platform. As you can see, the spheres that are generated on each spline represent the location that is closest to the character. The closest sphere will be where the character should start grinding. Cool. There's one more thing we need to consider when finding a point on the spline for our character to grind at, and that is the character's height. If we use the spline's location directly and move our character there, the character will end up inside the grinding platform, which obviously isn't what we want. To fix this, we need to apply an offset based on the character's height, specifically their half height. This ensures that the character grinds above the platform rather than through it. Let's calculate that height offset that we need to add to the grind location. Let's create a vector and name it character height offset. Okay, so in order to find this vector, we need to first find the direction that this vector should point in. The direction it should point in should be 90 degrees away from the surface of the grinding platform. It should look something like this. Luckily for us, we have the transform at the point on the spline, and a transform contains a rotation. With the rotation, we're able to find the forward, right, and up vectors at that point on the spline. The vector that we're interested in is the rotation's up vector, because that vector is pointing 90 degrees away from the surface of the grinding platform. Alright, let's call a function on the grind transform called getUnitAxis. This will return one of those direction vectors from the transform. For the first parameter, it needs an enumerator from the e-axis enum. We can choose either the x, y, or z axis. We're going to pass in z. The reason why we're passing in z is because we want the up vector, and the z-axis corresponds with the upwards direction. So x is forward, y is right, and z is up. So this function will return the z-axis vector, which is equivalent to the up vector from that transform. Next, we have to scale this vector so it has the same length as the character's half height. Let's define a float variable that stores the character's half height. I'm going to place it above the for loop because we'll be needing it again after the loop is complete. Okay, so in order to get the half height, we're going to use this character owner property. This character owner variable is a pointer to the character that owns this character movement component. In order to use this variable, we need to include the header file for the character class. Next, we need to call getCapsule component on the character owner. The reason why is because the character's half height is based on the half height of the capsule component that the character is using. The capsule component handles collision for the character. We need to include the header file for the capsule component. Now on the returned capsule component, we need to call getScaledCapsule half height to get the character's half height. This will also account for any scaling that was done on the capsule. Now that we have that, let's multiply this vector with the character's half height. We finally have the offset. Now let's add the offset to the location that's stored in grind transform. In order to do that, we need to call a function on grind transform called addToTranslation. Let's pass in our character half height offset. Alright, that's the code that adds the character's half height. Let's compile and run this to verify that it works. I'm going to jump and land on the grinding platform. As you can see, the grind locations are higher than they were previously, and the height offset matches the character's half height. Let's actually play this in slow motion so we have more time to see those grind locations. I'm going to open the console by pressing the tilde key. Now let's type in slow-mo 0.3. This will slow down the game speed to 30%. Alright, let's try this again. Now it should be clear that our code is working as intended. Awesome. Okay, so what's next? We need to come up with a way to filter out or ignore splines that we shouldn't grind on. What's considered a bad spline? The character shouldn't start grinding along a spline that's too far away. For example, if the character lands in the middle of this specific platform, they shouldn't start grinding on any of the splines because they're all too far away. So we should define a max distance that a spline component needs to be within in order for the character to potentially grind on it. I think a good idea would be to only consider splines that are within the radius of the sphere that we use to detect grinds. This radius value was used to detect grinds. Let's also use it to filter out splines. In the loop, let's write an if statement that filters out splines that are too far away. I'll explain it in a bit. So in this if statement, we use the distance function to find the distance between the character and the grind location. If this distance is greater than grind detection radius, we're going to skip this iteration of the loop. We're going to ignore this spline component and move on to the next one. Let's test this out. But first, we should change the color of one of these debug spheres so we can clearly see the difference between the two. I'm going to change the color of the grind location sphere to blue. Okay, let's compile and run this. Let's jump and land in the middle. As you can see, no spheres are generated on any of the splines because we're too far away from all of them. But once I land close to one of the splines, you can see that a blue sphere is generated on the spline. This indicates that the point that we found on the spline is within the distance of grind detection radius away from the character. Let's see what happens when we land in an area that's close to multiple splines. Let's land on a corner where two splines meet. Now you can see that two blue spheres are generated. Both of these splines are close enough to the character. Now that's a problem. We can't possibly start grinding on two splines at the same time. This leads us to the next problem that we need to solve. If we find multiple splines that are valid, how do we determine which spline is the best fit for the character to grind along? When the character lands in an area where multiple splines are within range, the best choice is the spline that the character is facing more directly towards. For example, if the character lands here, they should start grinding on this spline rather than that one, because their facing direction aligns more closely with the direction of the spline at that point. So we need to write some code to determine which spline is the character facing more directly towards. First, we should declare a pointer that points to the spline component, that is the current best spline component that the character should grind along. We should also declare an F transform that represents the grind transform that is currently the best. Let's also define a vector that represents the character's forward direction. This will be used to determine which spline is the best. Okay, so if we found a candidate for the best grind spline, here is where we'll determine if it's better than the spline we're currently evaluating. Else, let's set the best grind spline to the current grind spline. And let's set the best grind transform to the current one. So, in order to determine which spline is the best fit for the character to grind along, we need to calculate some kind of score for each spline component that we come across. This score is going to be based on the dot product between the character's forward vector and the forward vector of the grind transform. Let's talk a bit about how the dot product works so we have a better understanding. The dot product between two vectors tells us how similar two vectors are. If you take the dot product between two unit vectors that are pointing in the same direction, the result is going to be 1. As you rotate one of the vectors, the result of the dot product decreases. For example, if there is a 90-degree angle between both vectors, the dot product will be 0. If they point in completely opposite directions, the dot product is -1. So as you rotate the vector, it begins to approach -1, but once it passes that point, the dot product increases and starts to approach 1, where they're pointing in the same direction again, and the cycle continues. So how exactly does this help us? When we take the dot product between the character's forward vector and the forward vector of the grind transform, this tells us how much the character is facing the direction of the spline at that point we found. This can be used to score each spline we find. The spline component with the highest score will be the best fit spline component. Let's define a vector called grind forward. This will represent the forwards vector of the current grind transform. To get this, we're going to call the getUnitAxis function on the grind transform, and pass in the x-axis because the x-axis is equivalent to the forward vector. Let's define another vector called bestGrindForward. This will represent the forwards vector of the best grind transform, or the current best grind transform. Now let's score these. We now need to define a double called grindSplineScore. This will represent the score for the current grind spline. We will set it to the dot product of character forward and grind forward. Now let's define another double called best grind spline score, which will represent the score for the best grind spline. We will set it to the dot product of character forward and best grind forward. Now what we need to do is compare these scores. If the score for the current grind spline is higher than the score for the best grind spline, then the current grind spline should be the new best grind spline. Also, the current grind transform should be the best grind transform. Let's actually optimize this a bit. We don't need to find this best grind spline score every single iteration of the loop. We just need to calculate the score for the current grind spline. We also don't need to find this best grind forward vector every iteration either. Let's define best grind spline score here. The value we initialize it with doesn't matter. Let's also define best grind forward here. And the value we give it doesn't matter. Now in this scope, where the loop evaluates the first grind spline, let's find the value for best grind forward. Remember, it's the forward or x-axis vector of the best grind transform. Let's also set the value for best grind spline score. Remember, it's the dot product between character forward and best grind forward. Now in this scope, if we found a new best grind spline, let's set best grind forward to the new grind forward. Let's also set the new best grind spline score to the new grind spline score. Now we avoided having to recalculate best grind forward and best grind spline score in every iteration of the loop. Oh, one more thing, I almost forgot. The score should actually be the absolute value of these dot products. The reason why is because when we take the dot product between the two vectors, the sign of the result shouldn't matter. If the dot product is 1, that means the character is facing the same direction as the forwards direction of the spline. If it's -1, that means the character is pointing in the opposite direction. But a 1 and a -1 should be considered a perfect score. The score should decrease as the angle in between the two vectors approaches 90 or -90 degrees. Let's write some code to test and visualize this. If the best fit grind spline wasn't found, let's just exit out of this function. But if it was found, let's draw some debug spheres that trace along the spline that the character should follow. I'll explain how this code works in a moment. So what this code does is draw debug spheres along the spline at 30 units away from each other. This for loop creates a float called distance and adds 30 to distance after every iteration. We then use the distance variable to find the location at this exact distance along the spline. We're then going to draw a sphere at each distance along the spline. The sphere's radius is 15, which is half the distance. This way, the spheres will be positioned right next to each other. So this code essentially traces the spline's path with debug spheres, so it can clearly see which grind spline the character will grind along. Also, I know we're kind of using magic numbers here, but this code is just for debugging purposes. Let's also get rid of this debug code here, because we won't need it, and we've already seen this visualization. Let's compile and run this. Alright, I'm going to position the character at this corner here. I'm going to jump in this direction. As you can see, our code chooses the spline that the character is facing more towards. To further prove this, I'm going to jump and rotate my character in this direction. Now you can see that the other spline was chosen because it's more aligned with our character's current rotation. Let's slow down the speed so we can see this more clearly. Alright, great. We've completed our algorithm that selects the best fit spline for the character to grind along. Great job, guys. Okay, so what's our next step? Now that we've found a spline for the character to grind along, we should get our character to start grinding. When grinding, there is important data that we need to continuously keep track of every single frame. Data such as the current spline component that the character is grinding along, or the character's current distance along the spline component. We should come up with a way to encapsulate the data that's related to grinding. We're going to define a struct for this. Let's head to the custom character movement component header file. Let's define a struct called fGrindState. Let's add the uStruct macro in order to expose the struct to Unreal's reflection system. And since we added the uStruct macro, we're required to add this generated body macro at the top of the struct's definition. For the first property, we're going to declare a weak object pointer to a grinding platform. Let's name it grinding platform. This will keep track of what grinding platform our character is currently grinding on. Let's also add this uProperty macro so it's exposed to Unreal's reflection system, which keeps track of garbage collection. Let's declare another weak object pointer, but this time we'll have it point to a spline component. Let's name it grindSpline. This will keep track of the current spline component the character is grinding along. Don't forget to forward declare uSpline component. Now our next property is going to be a quaternion. I hope I didn't scare you away yet. Quaternions might sound intimidating at first, but I'll explain them in a way that's hopefully easy to understand. I'll teach you some of its most useful properties that will help our grinding application. A quaternion is just another representation of a rotation. Later on, I'll explain why and how we'll be using quaternions. Let's name it grind detection rotation. This will represent the rotation of the character at the moment we found a spline to grind along. Next, we'll define another quaternion called grind entry rotation. This will be the rotation of the spline at the point we initially found. The next property is going to be a vector called grind detection location. This will represent the location of the character at the moment we found a spline to grind along. Next, we'll define another vector called grind entry location. This will be the location on the spline at that point we initially found. Okay, just to further clarify things, the moment that we find the best fit spline, we're going to store the rotation and the location of the character at that exact moment. We're then going to store the location and rotation at that point on the spline that we found. This will be extracted from the best grind transform variable. Over time, we'll be rotating our character from this rotation to this rotation. We'll also be moving our character from this location to this location. Next, let's declare a float that keeps track of the character's half height. Remember, we need the character's half height in order to add the height offset to the grind location. Next, let's define a float called move to grind entry point duration. This variable will be the time we want it to take for the character to move from this location to this location. I set it to 0.2 seconds. It will also be the time it takes to rotate from this rotation to this rotation. The time it takes should be really short. 0.2 seconds is a good duration. Let's also define another float called move to grind entry point time elapsed. This will represent the amount of time that passed since we started moving to the initial location. This value will be important for interpolating our location and rotation. I'll explain more later on. Let's define another float called distance along grind. This will be used to keep track of the character's distance along the grind spline. The distance will be used to find new locations on the spline to move to. Next, let's define a boolean called b grinding forward. This will indicate if the character is grinding in the same direction of the spline. This is important. For example, if we found a spline and the spline is facing this direction, but the character is facing the opposite direction, the character should grind in the opposite direction of the spline's forward direction. So if this is false, meaning the character is not grinding in the spline's forward direction, we need to do some math to flip the grinding direction. Our final property is a boolean called b moving to grind entry point. This indicates if the character is in the process of moving to the grind entry location and rotating to the grind entry rotation. So there's two phases for grinding. Phase 1 is moving to the entry point, which is the initial grind location and rotation. The second phase is actually moving the character along the spline. I apologize if this was too much information to take in all at once, but we'll definitely go over each of these properties again as we assign them. Let's define a grind state member variable for our custom character movement component. And since we're keeping track of our grinding platform in this variable, we don't need this grinding platform variable. We should have never made this variable in the first place. My mistake. Let's go back to the custom character movement component.cpp file and update this code here so it defines a local grinding platform pointer. Let's name it hit grinding platform. Head back to the custom character movement component header file. This grind state variable should be at its default state whenever the game starts. So let's write some code that resets this variable whenever the game begins. We should override the begin play function. This begin play function is called whenever the game starts, so this would be a great place to reset our grind state. Don't forget to call the parent version of this function so it doesn't lose any base functionality. Now let's reset grind state. Let's assign the grind state properties. Let's head to the try_grind function. Scroll down here. We should first assign the grinding platform. Assign hit grinding platform to grinding platform. Next, let's assign the grind spline property. We should assign it to best grind spline, which was the best fit spline component that we found. Next, we should assign the grind detection location property. This should be equal to the character's current location. The next property we should assign should be grind detection rotation. This should be equal to the character's current rotation. We want this rotation to be in quaternion form, so let's call the getActorQuat function on the character owner. Next, let's assign the grind entry location property. This is the initial grind location that we're going to move the character to. We're going to assign it to the location that's stored in the best grind transform variable. Now let's assign the grind entry rotation property. This is the initial grind rotation that we're going to rotate our character to. We're going to assign it to the rotation that's stored in the best grind transform variable. Let's now assign the character half height property. Let's assign it to the character half height variable that we defined a while back. Next, let's assign the distance along grind property. So how do we find this distance? On our grind spline property, we can call the getDistance along spline at location function. This function returns the distance along the spline at a location we pass in. The location we should pass in should be our grind entry location property. This will give us the distance along the spline at that grind entry location. We also need to pass in world because we're passing in a location in world space. I almost forgot. Let's assign the move to grind entry point time elapse property to 0.0. Next, we need to assign the B grinding forward property. How should we determine if the character should grind in the same direction of the spline or in the opposite direction? When the character finds a best fit spline, we should find the angle in between the character's forward direction and the spline's forward direction. If the angle in between them is less than or equal to 90 degrees, the character should grind in the same direction of the spline. If the angle in between them is greater than 90 degrees, the character should grind in the opposite direction. What we can do is calculate the dot product between the character's forward vector and the spline's forward vector. If the dot product is positive, that means the angle in between them is less than 90 degrees. If it's negative, that means the angle between them is greater than 90 degrees. Just a side note, the dot product has a close relationship to the cosine of the angle in between two vectors. The dot product is equivalent to the product of the vector's magnitude and the cosine of the angle in between the two vectors. With that knowledge, let's assign B grinding forward. We're going to set it equal to this conditional statement, which finds the dot product of the character's forward vector and the forward vector of the grind rotation. Then checks if it's positive. Alright, now that we have this property set, we actually need to update the grind entry rotation based on this boolean. If B grinding forward is false, the character will grind in the opposite direction, which means we have to rotate the grind entry rotation by 180 degrees, so it's facing the opposite direction. Just to visualize this, if this is grind entry rotation, and the character is going to be grinding in the opposite direction, we should rotate grind entry rotation so it's also facing the opposite direction. So what we're going to do is combine multiple quaternion rotations. We're going to start off with grind entry rotation, but then add another quaternion rotation that rotates 180 degrees about grind entry rotation's local up vector. Let's code this up. I'll explain how this code works in a moment. Okay, so if B grinding forward is false, we're going to rotate grind entry rotation 180 degrees about its local up vector. The way we do this is by taking grind entry rotation and combining it with another quaternion rotation. The other quaternion represents an 180 degree rotation, and its axis of rotation is the up vector. So here we constructed a quaternion with an axis of rotation and the rotation angle. We concatenate or combine these two rotations with quaternion multiplication. Something important to remember is that the order in which we multiply these quaternions matter. Quaternion multiplication is not commutative. We want to take grind entry rotation and apply another rotation about the up vector in local space. To do that, grind entry rotation should be on the left side of the operation. If you wanted to apply the second rotation in world space, so the world's up vector, we would need to reverse this order. But we don't want that. We want the first rotation to be grind entry rotation, then we want to apply an 180-degree rotation about the up vector in local space. I really hope that makes sense. Also, you can just replace this with the UE_pi macro. This macro is equal to pi, and pi is 180 degrees in radians. I know this was a lot of information to take in. I hope I didn't confuse you. Please leave a comment if you need any clarification on anything. On character owner, we'll call a function named moved_ignore_actor_add. This function tells the character's collision system to ignore a specific actor that we pass in. We don't want the character to collide with the grinding platform, because that could interfere with how the character grinds along the grinding platform. We should have the character ignore collisions with the grinding platform entirely, just to be safe. Next, we're going to set B moving to grind entry point to true, because now we're going to begin the process of moving and rotating our character to the entry point. The next thing we're going to do is update our character's movement mode. Right now our character is in the falling movement mode. We want to update the movement mode to our own custom grinding movement mode. To do this, we need to call the setMovementMode function. For the first parameter, it needs an enumerator from the eMovementMode enum. Let's actually take a look at the definition for eMovementMode. As you can see here, this enum has the names for all the different movement modes that the character can use. There's a movement mode for walking, swimming, flying, and so on. The one that we're interested in is this move_custom movement mode. The reason why is because we'll be creating our own custom movement mode specific to grinding. Let's go back to the custom character movement component.cpp file. For the first parameter, we'll pass in move custom. The next parameter specifies which custom movement mode we want to use. We haven't actually defined any custom movement modes yet, so let's do that now. Open the custom character movement component.h file. Here, we'll define an enum called eCustomMovementMode, which will be the size of an int, add the uenum macro above it, and include the blueprint type specifier so it's accessible in blueprints. Now let's define our first enumerator, cMoveGrinding. This will represent our grinding movement mode. We'll also set a display name so it appears as grinding in blueprints. Finally, define one more enumerator for the max. Let's hide this one from blueprints, since there's no need to access it there. Whenever you develop new custom movement modes for your character, remember to add them to this enum. We're only working on grinding for this tutorial, so we're done with this enum. Now that we have that, let's head back to custom character movement component.cpp and pass in our grinding movement mode. Alright, let's recompile this just to check if we have any syntax errors. I'm going to press Ctrl B to build this project. Great, we have no errors. So we're mostly done with this function. Later on we'll add some optimizations and fix an issue that we'll encounter later, but for now, let's step away from this function and implement the next step for our grinding system. Let's scroll to the physFalling function. Remember, this is where we called try_enter_grind and stored the return value in this bEnteredGrind variable. Let's modify this function, so if the character entered a grind, we need to call a function called startNewPhysics. The reason why we're calling this function is because we want to restore the physics for the new movement mode that the character just entered. The physFalling function is called every frame and handles the movement logic for the falling movement mode. In a moment, we'll be defining a function that handles the movement for our grinding movement mode. So if bEnteredGrind is true, call start new physics, else call the parent version of this function to continue the following movement. Let's also remove this call to the parent version of physFollowing, since it should only be called if the character isn't entering your grind. Now let's talk about how movement is handled for our character. Let's go to the custom character movement.h file. Let's take a look at the parent character movement component class. I'm going to right click and select Go to Definition. Let's look for the move update functions. If you look here, these are the functions that handle movement for each of the different movement modes. There's one for the walking movement mode, the flying movement mode, and so on. The one that we're interested in is this phys custom function. We'll be defining our own custom movement function for our grinding movement mode, and this phys custom function will be responsible for calling it. So we should override this function in our custom character movement component class. Let's copy this function signature. Head back to our custom character movement component header file, and let's override phys custom. Let's call the parent version of this function. Now let's write a switch statement that switches on this custom movement mode variable. This custom movement mode variable keeps track of which custom movement mode our character is using. Well, we're only going to need one case label for this, since we only have one custom movement mode. So if custom movement mode is equal to cmove grinding, we need to call the movement function for our grinding movement mode. I'm going to name this function phys grinding. We haven't defined this function yet, so let's do that now. Let's head to the header file. Let's define our phys grinding function. It's going to be a virtual function that returns void. For the parameters, it needs a float called delta time and an int32 called iterations. Okay, this function will be responsible for most of the logic that handles grinding. Before we start writing the movement code, there are a few conditions that need to be met for this function to continue running. One of them is that delta time must be greater than a variable called min tick time. Delta time represents the amount of time that has passed between the current frame and the previous one. If delta time is smaller than min tick time, that means it's an extremely tiny non-zero value. It's so small that processing the frame can lead to errors. In that case, it's safer to simply skip this by doing an early return. Now our goal is to move the character from grind detection location to grind entry location, while also rotating from grind detection rotation to grind entry rotation. We'll achieve this by using a technique called interpolation. So what is interpolation? In game development, interpolation is the process of smoothly blending between two values over time. For example, blending between two animations. In our case, we'll be interpolating the character's position and rotation as they transition onto the grinding platform. We can accomplish position interpolation with a function called lerp, which is short for linear interpolation. The lerp function has three parameters. The first parameter is called a, which is the starting value. The second parameter is called b, which is the ending value. The lerp function will return a value in between a and b. The third parameter is called alpha, which is a float that ranges from 0 to 1. This determines how far between a and b the result should be. Let me explain with an example. If we use the lerp function to find a location in between location A and location B, and we pass in 0.0 for alpha, then the function is going to return the same location as location A. But as we increase this alpha value, the result is going to get closer to the location B. So if we pass 0.5 for alpha, the return location will be 50% of the way from location A to location B. So it'll return a location which is the halfway point between A and B. So by gradually increasing the alpha value over time, we can create a smooth transition to our grind entry location and rotation. However, when it comes to interpolating rotations, we're not going to be using the lerp function. We're going to use a different function called slurp, which is short for spherical linear interpolation. This function is useful for smoothly transitioning between two orientations. This is one of the major reasons why game developers use quaternions. Quaternions allow us to use slurp to smoothly interpolate rotations. The slurp function can't be used with Euler angles. Quaternions also avoid some of the problems that Euler angles suffer from, most notably gimbal lock. Slurp also ensures that the shortest path is used for rotating to another orientation. So those are a few examples of why quaternions are a powerful tool for game development. If you're interested in learning about rotations, I'd highly recommend the book called 3D Math Primer for Graphics and Game Development by Fletcher Dunn. This is an amazing book that teaches you 3D math from a game programmer's perspective. The book is also free, which is incredible. I'll leave a link to it down in the description. Sorry if that was a long explanation. I just wanted to make sure you have a clear understanding of quaternions and how interpolation works, because that's what we'll be taking advantage of right now. Alright, let's get to coding. Let's define a vector that represents our previous location. We'll need this to calculate our delta location that will be used to update our character's location. So we need to assign our character's current location to this variable. So let's get the updated component variable and call getComponentLocation. This is the same thing as calling getActorLocation on the character owner, but this is the convention for this context. Let's define another vector that will represent the new location for the character. This should be empty for now. And let's define a quaternion that represents the new rotation for the character. This should also be empty. Next, we need to check if the character is currently in the process of moving to the grind entry point. Right now, we're going to focus on the case where this is true. So if the character is moving to the grind entry point, the first thing we're going to do is accumulate the time that has passed since the character began moving to the grind entry point. We do this by adding delta time to the move to grind entry point time elapsed variable in grind state. So this delta time variable is the amount of seconds that has passed between the previous frame and the current frame. This move to grind entry point time elapsed variable keeps track of how much time has passed since the character made that initial contact with the grinding platform. We add delta time because that helps us add the total amount of seconds that passed. This variable is going to help us calculate the alpha value that we need for our interpolation functions. Let's calculate alpha right now. So alpha is going to be equal to move to grind entry point time elapse divided by move to grind entry point duration. Remember, this float represents how long we want it to take for the character to move and rotate to the entry point. This alpha value is the percentage of how close the character is to the entry point, and we get that by dividing the time elapsed with the total time, or the duration. We should also clamp this value between the 0 and 1 range, because alpha shouldn't be outside of this range. Also, just to be safe, let's add an assertion that this move to grind entry point duration variable should be greater than 0. It should never be 0 because that will cause a divide by 0 error. Also, it wouldn't make sense for the duration to be negative. So if this fails, our game will crash and give us this message. Next, let's find the new location for our character. Here, we'll be using that lerp function that I talked about earlier. Let's call lerp. The first parameter is A, which is the starting value. In this case, it's the starting location that we want the character to move from. Let's pass in grind detection location. The second parameter is B, which is the ending value. We're going to pass in the location where we want our character to move to. Let's pass in grind entry location. The next parameter is the alpha value. Let's pass in alpha. So this function is going to return a location in between grind detection location and grind entry location. And alpha is going to determine how close it's going to be to grind entry location. Alright, we found the character's new location. Now we're going to find the new rotation for the character. Let's call the slurp function. For the first parameter, it needs the quaternion that represents the initial orientation that we want to rotate from. Let's pass in grind detection rotation. The next parameter needs the orientation that we want to rotate to. Let's pass in grind entry rotation. The next parameter needs alpha. Alright, we have the new rotation. Now, let's actually move and rotate our character to these values. Let's call a function called safe_move_updated_component. This function will move our character to the location and rotation that we provide it with, and it will also handle collisions. For the first parameter, it needs a vector that represents the delta from the previous location to the new location. This is the displacement from the character's previous location to the new location that we want to move the character to. Let's define this vector. So delta is going to be equal to the new location subtracted by the last location. Let's pass this into the function. The next parameter needs a quaternion that represents the new rotation for the character. Let's pass in the new rotation quaternion we defined earlier. The next parameter is a boolean called bSweep. This indicates if we want to check for collisions when the character is moved. We're going to pass in true for this because we don't want other objects or characters to be able to move through the character when it's grinding. I'm also planning on making the character stop grinding if it collides with another object. The next parameter needs a hit result object. Let's define one and pass it in. It should be empty. So if this move results in a collision with another object, this hit result variable will give us information about the collision. The next thing we need to do is update the velocity for the character since it moved. So to update the velocity, we need to set the velocity variable equal to the character's current location minus the last location. And we divide the components by delta time. There are a few more things we need to add before testing this. Let's iterate the iterations variable. We also need to set B just teleported to false, because this was a regular movement. We didn't teleport to a new location. Let's compile and test this out. As you can see here, when the sphere collides with the platform, and if the character is close enough, the character will start rotating so their orientation aligns with grind entry rotation. The character's location will also start interpolating to the entry point that we found on the spline, which is grind entry location. Let's slow down the movement so you can kind of get a better look at what's happening. Press the tilde key and type in slow-mo 0.1. Press enter. So once the sphere collides with the grinding platform, and once the character is close enough to the detected spline, the character's rotation and location will start interpolating to the entry point that we found on the spline. Let's try this one last time, but this time I'm going to increase the radius of the sphere, just so you can clearly see what's happening. Let's go to the blueprint for our third-person character. Let's type in grind detection radius and increase it to 100. I'm going to slow down the speed again. The sphere is going to collide with the platform, and the character's location and rotation will interpolate over the duration of 0.2 seconds. Awesome. Hopefully you guys are understanding what's going on and how we got here. Leave a comment if you have any questions. I'm going to reset the grind detection radius to its default value. Alright, so what's our next step? Our next step is getting the character to actually grind. Very exciting stuff. It took a while to get here, but we're finally here. We need to know when the character finished interpolating or finished moving to the grind entry point. Once the character finished moving to the entry point, that's when the character needs to start grinding along the spline path. A way we could find this out is by checking if this move to grind entry point time-elapse variable is greater than this move to grind entry point duration variable. If the time elapsed is greater than the duration, that means the character completed moving to the entry point. So we should check for that. Let's override a function called onMovementUpdated. Let's go to the custom character movement component header file. Now let's override the onMovementUpdated function. Here's the function signature. Let's define this. As the name suggests, this function is called when the character's movement has been updated. This would be a good place to check if the character is already at the grind entry point. Let's first call the base version of this function. Now let's check if the character is currently moving to the entry point and check if the time elapsed is greater than the duration. If that's the case, we're going to set B moving to grind entry point to false. Alright, let's head back to the phys grinding function. This else block is where we'll be writing the code that makes the character grind. Before we move forward, let's define a variable that represents how fast the character should grind. Let's go to the header file. Let's define a float property called grind speed. The default value will be 600 centimeters per second, but feel free to choose whatever value you want. Let's head back to the else block in phys grinding. First, we need to check if the character is grinding in the forwards direction or the backwards direction along the spline. If the character is moving in the forwards direction, we need to move the character to the spline's endpoint. We need to move the character to the max distance along the spline. So here, we're going to update the character's distance along the spline in the positive direction. So it's going to be distance along grind, and we're going to add our grind speed multiplied by delta time. So every frame, we need to increase the character's distance by their speed multiplied by delta time. For example, if the character's current distance along the spline is 0.0, and the character's grind speed is 600 centimeters per second, but delta time is 0.5 seconds, that means only 0.5 seconds has passed. The character's distance shouldn't increase by the full 600 centimeters. The character's current distance should increase by 300 centimeters because 0.5 seconds has passed. So we increase the current distance by grind speed multiplied by delta time. Alright, if the character is not grinding in the forwards direction, the character's distance along this spline should be approaching 0.0. So we're going to copy and paste this. But change the addition to a subtraction. Now that we've found the new distance for our character, let's find the rotation and location that the character should have at the current distance along this spline. Let's find the new rotation first. So in order to find the rotation at the current distance along the spline, let's call a function on the grind spline called getQuaternion at distance along spline. If you forgot what grind spline is, it's the spline component that the character will be grinding along. For the first parameter, it needs the distance. Let's pass in distance along grind. The second parameter needs an enumerator from the E-spline coordinate space enum. We want this rotation to be in world space, so let's pass in the world enumerator. We now need to check if the character is grinding in the backwards direction. If that's the case, we need to rotate the quaternion 180 degrees about its local up vector. This should look familiar to you. We did something similar when we were calculating the grind entry rotation. I did a whole explanation on quaternion multiplication. Alright, we have the new rotation. For the new location, we're going to call a similar function called getLocation at distance along spline. It's going to use the same arguments as the quaternion function. Same arguments, same reasons. Now what we need to do is add an offset based on the character's half height, which is the new rotation's up vector multiplied by that character's half height. We did something similar when we were calculating the grind entry location, and I did a whole explanation on how that works. Let's compile and test this out. Great, our character now grinds on the grinding platform. Let's angle this and see if it still works. Awesome, still works. It currently stops once it reaches the end of the spline, so let's figure out how to handle this. So what should the character do once they reach one of the endpoints on the spline? Well, it depends. If the spline contains a loop, so if the grinding platform has a circular path, the character should just loop around the spline. So if the character is moving in the forwards direction, their distance will be increasing. Once the character meets the max distance along the spline, then the character's distance should wrap around from 0. If the character is moving backwards, their distance is decreasing. So once their distance reaches 0, that is when their distance should wrap around from the max distance along the spline. That handles the case where the spline is looped. But what if the spline isn't looped? In that case, the character should just begin to fall. So once the character meets one of the endpoints, then we should set the movement mode to falling. Just to be clear, when I refer to the spline's endpoints, what I'm talking about is the point on the spline where the distance is 0, or when the distance is equal to the length of the spline, so the max distance along the spline. So first, let's find the length of the spline that the character is grinding along. Let's define a float called spline length. We can easily find the length by calling the getSplineLength function on the spline. Next, we should check if the character has passed one of the spline's endpoints. Let's define a boolean called bPassEndpoint. The way to check if the character passed an endpoint is by checking if the character's current distance is greater than the spline length. Or if the current distance is less than 0. We need to think about when the character should stop grinding. The character should stop grinding if they passed one of the endpoints and the spline isn't looped. That's when the character should just start falling. So let's check if bPassEndpoint is true, and if the spline is looped. We can easily check this by calling the isCloseLoop function on the spline. In this case, the rotation should remain the same, so let's set new rotation equal to the character's current rotation. In terms of the new location, I'm just going to have the character move in the forwards direction at the same speed. So it's going to be last location plus the character's forward vector multiplied by the grind speed and delta time. This will move the character in the forwards direction. Let's also define a bool that indicates if the character should continue or stop grinding. Let's scroll up a bit, and here we'll define a bool called b should continue grinding. It's going to be initialized to true. Let's scroll back down. Now, if the condition is true, the character should stop grinding. So let's set b should continue grinding to false here. All of this code right here should be executed if the character needs to continue grinding. So let's wrap this in an else block. Inside of this else block is where we calculate the new rotation and location of our character if they should continue grinding. Let's handle the case where our spline is looped. So if our spline is looped, we should wrap the character's distance between 0.0 and the length of the spline. We can do this by calling the static function called wrap. The first parameter needs the value that we're wrapping, so let's pass in the character's distance. The next two parameters are the min and the max values for our range. We want to wrap this in between 0.0 and the length of the spline, so let's pass those in. So if our character is grinding backwards, their distance decreases. If their distance becomes negative, this means the character passed an endpoint, so we should wrap it around its max value, which is the length of the spline. This wrap function does that for us. If the character is grinding in the forwards direction, the distance will increase, and once the distance passes the length of the spline, then this wrap function will wrap it back to 0.0. Alright, so after all of this movement logic is done, we should check if the character should continue grinding. If the character should stop grinding, then they should begin falling. Let's scroll down to the end of the function definition. So here, let's set the movement mode to falling if b should continue grinding is false. Okay, before we test this out, let's draw a debug string onto our screen that tells us the character's current distance along the spline. This will help us visualize and better understand how the distance and wrapping works. Let's call the drawDebugString function. The first parameter needs the uWorld object, so let's call getWorld. The next parameter needs the location where we want to put our string at. Let's display at our character's current location, So let's call it getActorLocation. The next parameter needs the string that we want to print. Let's define a variable for this. I'm going to use the printf function to format the string. The string is going to contain the distance along grind variable. So let's type in distance along grind. And let's insert the variable here. It's a floating point type, so we need to add %f. Now for the second argument of this function, let's pass in our distance along grind variable. So our distance along grind variable will be inserted into the string right where the %f is. It's very similar to the printf function in the C programming language. Let's pass in the string. The next parameter is a pointer to an actor called testBaseActor. To be honest, I'm not familiar with what this parameter is for. I never had to use it. I'm just going to pass in null pointer. The next parameter needs the color that we want our string to be. I'm going to use white. The next parameter needs the duration for the string. Let's pass in 0.0 because we just want to create it, display it for the current frame, then destroy it, so we're constantly updating this every frame. The next parameter is a boolean that indicates if we want a drop shadow. I'm going to pass in true. The final parameter needs the font scale. I'm going to pass in 2.0. Let's compile and test this out. Awesome. The character falls off once they pass an endpoint. I'm going to move this over here and demonstrate this again. So when I grind in the forwards direction, our character's distance increases. Our debug string shows this as the character moves towards the max distance of the spline. Let's try grinding in the backwards direction. As you can see here, our debug string shows that our character's distance decreases. And once it reaches 0, our character begins to fall. Alright, let's test if this works for loop splines. Let's place another grinding platform in the level. Drag and drop an instance of BP grinding platform into our level. Let's change the static mesh to the cylinder, and choose the cylinder that is facing upright. I'm going to scale it a bit along the z-axis. Now press the N key to make a snap to the surface of the floor. Let's increase the scale along the XY plane so it fits nicely on top of the other surface. Adjust the location a bit so it's in the middle. Alright, what I'm going to do now is hide all of the other actors on our level so we're only able to see this grinding platform that we're currently working on. To do this, let's select the grinding platform, right-click, and choose Show Only Selected. Now our grinding platform is the only visible actor in our level. This is going to help out a lot. But at the moment, we're only able to see the outline of our platform. The reason why is because we hid all of the lighting in our level, so our level is completely dark. To fix this, let's change our view mode to unlit. Much better. Let's add a new grind spline to our platform. Make sure our platform is still selected. Navigate to the Details panel and search for grind splines. There it is. Now click the plus to add a new one. Remember, we need to select our platform again in order for the spline to show up. So click on the platform. Now there's our newly created spline. Let's go to the top view and select the new spline component. What we need to do now is drag the spline all the way to the edge of the platform. Make sure it aligns with this x-axis or the y-axis. This will help out a lot. Now let's switch to the right side view and let's raise the spline so it's right above the platform. Let's switch back to the top view. Zoom out a bit. What we need to do is select the second spline point and drag it to the other side of the platform, but it looks kind of tricky from the top view. So let's switch to the right view and select the spline point. Now we need to drag it to the other side of the platform. Alright, cool. Let's select our spline again. Now look for the closed loop option. Here it is. We're going to check this box so it becomes a closed loop. Awesome. Let's select our spline component again. What we need to do next is add 2 more spline points. So somewhere in the middle of the spline, we're going to right click and choose add spline point here. Great. Now let's drag it to the right side of the platform. Make sure it aligns with this green y-axis. Let's do this again, but this time we need to drag it to the left side. Again, align it with the green y-axis. This way, we have 4 spline points from the center that are 90 degrees away from each other. Now, here comes the tricky part. We need to adjust the spline point tangents so the spline curves around the edge of the platform. So, play around with these tangents until you roughly make a circular path around the platform. I know there's some kind of equation to find the tangent of a circle. I might write some code that lets the user just check a box to make a circular path based on the radius, but that'll have to wait for another day. Alright, I think that looks good enough. Let's select the platform again, right click, and select Show All Actors. Let's change our view mode back to lit. Let's test this out. As you can see, our distance increases, and once it reaches the max distance, it's going to wrap around back to 0. Let's try this again in the opposite direction. The distance now decreases, and once it reaches 0, it'll wrap around to the max distance. Awesome job, guys. Oh, and don't worry about the character's legs bending and hanging off the other side. That's happening because the character's animation blueprint is using inverse kinematics for the legs, which we'll disable later on in this tutorial. Alright, awesome. We figured out how to move our character along splines that are open or closed loops, which is the foundation for our grinding system. So what's next? There is one issue with our grinding system that we haven't addressed yet. Let me demonstrate this issue. I'm going to rotate this platform so it's flat. When our character grinds and reaches an endpoint, there is a good chance that the character is going to get stuck or instantly move to another spline and grind again. They're supposed to start falling once they reach the endpoint. So why is this happening? The reason why this is happening is because once the character starts falling, the try enter grind function is going to execute again. This is going to make the character start grinding again on the spline that they're trying to fall away from. So we need to find a way to make the character ignore splines that they're moving away from. More specifically, we need to ignore splines that are not in the direction of the character's velocity. So if the character meets an endpoint and begins to fall, and the character detects a spline, we should create a vector from the character to the point on the spline that we found. We also need to get the character's current velocity. If this vector is pointing in the opposite direction of the velocity, we should ignore the spline and not try to grind on it again. We can check this by taking the dot product of the two vectors and looking at the sign. Negative means they're pointing in opposite directions. So let's head back to our custom character movement component.cpp file, and let's scroll to the try enter grind function definition. So here in this for loop is where we compared splines. For each spline, we found the location on the spline that is the closest to the character. That location is stored in this grind transform variable. It's also the location on the spline where the character could potentially begin grinding at with its half-height offset. Before we add the half-height offset here, we should create that vector that starts from the character's location to the location that we found on the spline. Let's call the vector character to grind location. And set it equal to the location stored at grind transform minus the character's location. Then, we can check if the dot product between the character to grind location vector and the velocity is negative. If it's negative, we're going to ignore this spline and move on to the next iteration of this loop. So what we just did is write some code that checks if the character's velocity is facing the same direction as the grind location relative to the character. If the dot product is negative, that means the character is moving away from the location on the spline. If the character is moving away from that location, we should just ignore the spline and not attempt to grind on it. That most likely means the character just finished grinding along the spline. I hope that made sense. Let's compile and test this out. Now the character doesn't get stuck at an endpoint and gracefully begins to fall. Cool. So what's next? When the character exits a grind, they can still pass straight through the grinding platform with no collision, which shouldn't happen. This happens because earlier in the try to grind function, we called move ignore actor add to make the character ignore collisions with the platform while grinding. To fix this, we need to restore collisions with the platform once the character is no longer grinding. We should do this right after the movement mode is switched from the grinding movement mode to another movement mode. So what we should do is override a function called onMovementModeChanged. Let's go to the header file and override the function. Here's the function signature. Now let's define this. So this function is called right after the character's movement mode changes. It's supplied with parameters that tell us what the previous movement mode was. We want to check if the character stopped grinding, because that's when we need to restore collisions with the grinding platform. We do this by checking if the previous movement mode is equal to move_custom. This means the previous movement mode was a custom movement mode. This previous custom mode parameter tells us which one of the custom movement modes it was. We need to check if it was the grinding movement mode. Remember, we defined this grinding movement mode in an enum that stores the names for all of our custom movement modes. Okay, so here is where we'll restore collision with the grinding platform. We need to call a function on character owner named moveIgnoreActorRemove. Let's pass in the grinding platform. So if the previous movement mode was a custom movement mode, and the custom movement mode was the grinding movement mode, we need to restore the character's ability to collide with the grinding platform that they were previously grinding on. Oh, and don't forget to call the base version of this function. Let's compile and test this out. Let's grind, and once we exit out of the grind, we should be able to collide with the platform again. Great. Our next goal is to implement the ability for our character to jump out of a grind. Currently, if the character is grinding, and we try to make the character jump, nothing will happen because jumping hasn't been enabled for our grinding movement mode. So let's enable jumping. Let's go to the header file for our custom character movement component, and let's override a function called canAttemptJump. Here's its signature. So the way we're going to implement this is by returning true if the base version of this function returns true, or if the character is currently in the grinding movement mode. So if the base version says it's okay to jump, then return true. But if that's false, allow the character to jump if they're in the grinding movement mode. This code here checks if the character is currently grinding. We should do better and refactor this check into its own function. I'm going to name this function isGrinding. Let's create this function. So open the header file and let's declare isGrinding. It's going to be a public function. It's also going to be const and return a boolean. We'll just add the code that we wrote before. Alright, let's compile and test this out. I'm going to jump on the looped grinding platform. Now I'm going to try to jump by pressing the spacebar. And now it works. Awesome. What we're going to do next is disable movement input while the character is grinding. When the character is grinding, the player still has the ability to move the character around with the WASD keys as if the character were walking. We shouldn't allow the player to do this. There's a function we need to override called addInputVector. Let's open the header file for our custom character movement component and override addInputVector. Here's the signature. So this function is inherited from the pawn movement component class, and the purpose of this function is to move the character based on the player's input. Before this function is called, the player's input is converted to world space vectors. Those vectors are then passed into this function and will move the character based on those vectors. What we should do is call the parent version of this function only if the character is not grinding. So if the character is grinding, this function is just going to ignore the player's input and not execute at all, and the player won't be able to move the character with directional input. Jumping is the only movement that's allowed. Let's compile and test this. I'm going to grind, and now I'm going to try to move the character with the WASD keys. Great, nothing is happening when I try to move the character, which is exactly what we want. Now that we have that done, there are a few more checks that we should add to complete our grinding system. Let's scroll to the try_enter_grind function. In this for loop, we should check if the grind spline is null. The grind spline should never be null. If it is, then we made some kind of programming error. So let's add an assertion here that checks if the grind spline is valid. If it isn't, we'll just terminate the game and print this message. Alright, awesome. What I want to do next is write some code that will make our characters stop grinding if they encounter an object that's blocking their path. For example, if two characters are grinding on the same platform, but in opposite directions, I want to stop those characters from continuing to grind once they collide with each other. Alright, so here in the fizz grinding function, after the velocity is updated, I'm going to check if this movement resulted in a blocking hit. We do this by checking if the B blocking hit variable in the hit result is true. Remember, in this safe_move_updated component function call, we pass in this hit result. Now we have information about any hit that occurred during this movement. If B blocking hit is true, that means something blocked this movement. In this case, I'm simply going to set the movement mode to the walking movement mode so the character stops grinding. This should also be an if-else-if chain. Alright, let's compile and try this out. So what I'm going to do first is add an instance of our third-person character into our level. Let's find the blueprint for the third-person character and drag it into our level. I'm going to place it right above the edge of our cylinder grinding platform. This way, the character will fall and start grinding once we play our game. Let's start our game. Now that third-person character is grinding, I'm going to try to grind in the opposite direction. Great, both characters stopped grinding once they blocked each other's path. Nice work. The next thing I want to do is add a small optimization to our code. So here in the try_enter_grind function, in this for loop, we check the distance between the character and the location that we found on each spline that we iterate through. We compare the distance with the grind detection radius. We can optimize this by comparing the distance squared instead of the distance. Let me explain how this works. When we're finding the distance between two locations, the distance formula first finds the displacement vector between the two locations. Next, the formula calculates the size of this vector. The size of this vector is equivalent to the distance between the two locations. The equation to find the size or the magnitude of a vector is the square root of the sum of the squares of each of the vector's components. So the size of a 3D vector is the square root of the x component squared plus the y component squared plus the z component squared. It's from the Pythagorean theorem, an equation you thought you'd never see again once you graduated, but it turns out you can't make video games without triangles. Anyways, now here is where we can make an optimization. So this square root operation is actually an expensive math operation for the CPU to execute. If possible, we should avoid computing the square root, especially multiple times every frame. A way we can avoid this is just by getting rid of the square root. But now we don't have the distance. we now have the distance squared between the two locations. This is perfectly fine, but you also need to square the value that you're comparing the distance to. So here in our code, we're trying to find out if the distance between the character and the location on the spline is greater than the grind detection radius. We can optimize this by changing this distance function to the distance squared function. This will get rid of that square root, but since we're squaring this side of our comparison, we also need to square the other side of our comparison, so we need to square the grind detection radius. I really hope that makes sense, and you understand why finding the distance squared is more optimal than finding the distance. We can actually do better and cache this value instead of recalculating this over and over again every frame. This value is never going to change while we play our game. So let's remove this and replace it with a variable that represents the grind detection radius squared. I'm going to name it grind detection radius squared. Let's declare this variable in the header file. It doesn't need to be initialized with a value. Let's go back to the implementation file and go to the begin play function. Here is where I'm going to assign a value to grind detection radius squared. Let's set grind detection radius squared to grind detection radius squared. Let's compile and test this out. Yep, everything works as expected. Alright, cool. We've completed that optimization. So there's one more improvement I want to make with regards to movement. Specifically, an improvement to how the character transitions onto a grinding platform. Currently, when the character finds a spline to grind along, they move to the point on the spline that is the closest to their location. This causes the movement to feel like it stopped for a moment before grinding. Shout out to Jamshed on LinkedIn for pointing this out. The reason why it feels that way is due to the entry point being right below the character, causing the character to move downwards before grinding. We can improve this by finding an entry point further down along the spline, instead of an entry point that is the closest to the character. This way, it will feel like the character is moving forward as they're transitioning onto the platform, rather than feeling like the character stopped for a moment. So we'll first find the closest point, then add an offset based on the time we want it to take for the character to transition onto the platform. Let's save and close the project. Let's open the custom character movement component.cpp file. We need to scroll to the try-enter-grind function and find the code where we initialize the grind state variable. What we need to do first is reorganize some of this code because some initializations need to happen before others. So let's move the character half-height initialization up here. We also need to move the B grinding forward initialization up here. But we also need to update this line of code. Instead of taking the dot product between the character's forward vector and grind entry rotation's forward vector, we're going to change this to best grind transform's forward vector. Remember, the best grind transform variable is the transform at the point on the spline that is the closest to the character's location. Our next step is we're going to move the distance along grind initialization up here. I'm going to modify this initialization so it finds the distance along the spline that is the closest to the character. Don't worry, this is all going to make sense. Now that we have that initial distance along the spline, we're going to add an offset to this distance, and this offset is going to be based on the time we want it to take for the character to fully transition onto the platform. Remember earlier when I said we want the entry point to be further down along the spline. The offset that we're about to add is going to help us find that entry point. So here, we're going to check if the character is grinding in the forwards direction. We're going to add an offset to the distance. The offset is going to be grind speed multiplied by the move to grind entry point duration variable. So what adding this offset did is give us the distance along the spline that is 0.2 seconds into the future. Because remember, we initialized this duration variable to 0.2 seconds, or 200 milliseconds. I should have just said 200 milliseconds. So here in this else block, if the character is not grinding in the forwards direction, we're going to subtract that offset instead. Our next step is to wrap the distance, just like we did over here when we were finding the location and rotation for the next frame. So if grind spline is a closed loop, we're going to wrap the distance between 0 and the spline's length. The next thing we need to do is update how we find grind entry rotation. So let's delete this. So the way we're going to find grind entry rotation is by using the get quaternion at distance along spline function. We're going to pass in the distance along grind variable. Don't forget to rotate this quaternion 180 degrees about its up vector if the character is not grinding in the forwards direction. Our final step is to update how we found grind entry location. So let's delete this code. We'll find the location by calling get location at distance along spline. Again, we'll pass in distance along grind. Don't forget to add the character half height offset. Let's move the detection initialization up here where it makes more sense. Alright, let's compile and test this out. I'm going to slow it down. I think this looks great. Now it moves forward from the very beginning thanks to the offset we added. Perfect. Don't worry, you'll start noticing the improvement once we add grinding animations. So, in terms of the movement logic for our grinding system, we're pretty much done. All we need to do now is implement the visual elements for our grinding system. We need to add the grinding animations for our character, and implement the logic that plays the correct animations. After that, we need to add the spark effects that activate whenever the character grinds. We'll be developing an actor component dedicated to activating that Niagara particle system. We'll also go over how to put together this Niagara system that shoots out sparks and is influenced by the character's velocity. If you're not interested in any of that, then I think you have all the information you need for this grinding system and can stop here. But for those of you who want to stick around, let's move on to the animations. So in the description of this video, there's a zip file with all of the animations in UAsset form. Just download that, extract it, copy and paste the extracted folder into the contents folder of your project. You have to do this within your file explorer. It won't work if you try to import it with Unreal Engine's interface. Now that we have our animations imported, let's head back to the custom character movement component.h file. What we want to do next is make our isGrinding function callable in Blueprints. We want to expose this function to Blueprints and be able to call this function in our animation blueprint. We want our animation blueprint to start playing the grinding animations if this function returns true. So we'll need to add the uFunction macro and pass in the blueprint callable specifier. Now we can call this in Blueprints. Let's compile and run this. Let's look for the animation blueprint that our third-person character is using. Let's open the blueprint for the third-person character. Let's move our mouse down here to this anim class property. Here it shows that the animation blueprint the character is using is called ABP Unarmed. Let's click this button to browse to the animation blueprint, and here it is. It might use a different animation blueprint depending on which Unreal Engine version you're using. I remember on an older version of Unreal, their third-person template used an animation blueprint called ABP Mani. So just make sure you open the correct animation blueprint for your third-person character. Let's add a new variable to this animation blueprint. Click this add button, and it's going to be a boolean called isGrinding, which will keep track of if the character is grinding or not. The next thing we need to do is figure out how we're going to update this variable every frame. The way that this template does it is by updating all the variables here in this event graph. The variables are updated in this blueprint update animation event. Normally, I wouldn't update these variables in the blueprint graph. I would handle this in C++ through the parent animation instance and update the variables inside the native thread-safe update animation function. However, for this tutorial, I just want to quickly get the grinding animations working with the third-person template. Going over how to properly implement an animation instance and write all the logic for it would make this tutorial much longer than it already is. So we won't be doing this. Sorry about that. Let's compile this. Before we update the isGrinding variable, we need to modify this variable here called movement component. This movement component variable stores an object reference to the character movement component that our character uses. We need to change this so it uses our custom character movement component and not the base character movement component. We need access to the isGrinding function that is in the custom character movement component class. So let's change the type. It's going to be an object reference to a custom character movement component. Let's compile. Now we have some errors because the event graph is still using the base character movement component. Let's fix that. So delete this. Let's get the base character movement component from the character. Next, we need to cast this to a custom character movement component. Now we need to set the movement component variable to the casted movement component. Let's also plug these in. Press compile. Now here is where we'll update the isGrinding variable. Here in the blueprint update animation event, there is a sequence node that connects to the code that updates the variables. Let's add a new pin to the sequence node. This pin will be dedicated to updating our isGrinding variable. Let's get the movement component variable. Now here is where we'll call the isGrinding function that we implemented in C++. Let's set the isGrinding variable to the isGrinding function's return value. Now let's connect these pins and press compile. Awesome. Now we have the data we need to determine if the character is grinding. Next, we need to head to the atom graph and write some logic that will play grinding animations if the isGrinding variable is true. Let's open the main state machine. Let's create a state for our grinding logic. Let's name it grinding. The only way to get to a grinding state is from a falling state, so we need to add a transition from the for loop to the grinding state. We should also add a transition from the jump state. We can actually do better. Rather than having these links, let's get rid of them and let's create a state alias for our grinding state. If you're not familiar with state aliases, they're just another way to reduce clutter and improve organization when creating transitions between states. So, what states are allowed to transition to the grinding state? You can transition to the grinding state from the for loop and jump states. So let's click on the state alias, go to the details panel, and check the two states. Another question we need to ask is, what states can the grinding state transition to? You can only fall after a grind, so let's go to the two falling state aliases detail panel and check grinding. Okay, so how can a state transition to the grinding state? What is the grinding state's transition rule? The only rule is the isGrinding variable needs to be true, so let's add that transition rule. We also need to add another transition rule for the land state. IsFalling needs to be false, but isGrinding needs to also be false, because if the character is grinding, they're also not falling. But we want it to transition to the grinding state, not the land state, so let's add that. Press compile. Now let's head back to the main state machine. What I'm going to do is rename this to grindland. And I'm going to add another state called grind loop. When the character transitions into the grinding state, I first want to play an animation of the character landing onto the grinding platform. So let's open up the grindland state. Here is where we'll plug in the grindland animation into the output animation pose. Let's search for the animation in the asset browser. Here it is. Let's drag and drop it. Then plug it in. Let's open the animation to see how it looks like. It's just a simple landing animation. I'm sorry if these animations are really bad. I'm not an animator, and I couldn't find any free, high-quality grinding animations that I could provide you guys with, so I just made some modifications to existing animations. Sorry about that. Let's close this. Let's go back to main states. After the landing animation is complete, I want to immediately play the grind loop animation. Let's open this grind loop state and plug in this grind loop animation. Let's check out this animation. So we want this animation to loop for as long as the character is grinding. Let's close it. Click the animations node, go to its details panel, and check the loop animation box. Alright, go back to main states. Now we want the grind loop animation to play immediately after the grind land animation finishes. So click on this transition rule, go to the details panel, and check this box that says automatic rule based on sequence player and state. This will make sure it will automatically transition once the animation finishes. Press compile. Let's test this out. Let's move this guy out of the way. Oops, there's something wrong. The grinding animations seem really off, And the reason why is because of this control rig. The grinding animations don't seem to work properly when this control rig is applied, and I honestly don't know why. I tried to add a condition here that the IK trace should be disabled if the character is grinding, but that doesn't seem to work. What we're going to do instead is skip this control rig completely if the character is grinding. We don't need inverse kinematics if the character is grinding anyways, so let's cache the main states pose. Let's also add this blend poses by bool node so the control rig is executed only if the character is not grinding. Oh, and one more thing. There's something I forgot to do. Let's click on the toFollowingState alias. I forgot to check the grind loop box. The character should be able to transition into the following state from the grind loop state. If this box isn't checked, then the character won't be able to break out of the grind loop animation. Let's also click on the toLand state alias, and we need to check the grind land and grind loop boxes. If we leave these unchecked, then the character won't be able to break out of a grinding animation if something is blocking their path. Let's compile and try this again. Okay, awesome. Everything is working as expected. Alright, we're almost done, guys. The last thing we need to do is add the spark effects that activate at the character's feet while they're grinding. I tried my best to make these grinding effects look similar to the grinding effects seen in the game Sunset Overdrive. Sunset Overdrive was a big inspiration for this grinding system. Let's create a new actor component that will be responsible for the grind effects. Click Tools and click New C++ class. This class is going to be inherited from the actor component. Let's name it Grind Effects component. Click Create. Let's close the project. Now that we've created our Grind Effects component, let's create an instance of this component for our character to use. So head to the header file for the third-person character class. Let's also forward declare the Grind Effects component class. Now we need to declare a member variable for the Grind Effects component that the character will use. It's going to be a pointer to a Grind Effects component. If you're wondering about what a T-object pointer is, it's basically a templated smart pointer that was introduced in Unreal Engine 5. Epic Games recommends using T-object pointer instead of raw pointers, which is why I find it really strange that they still use raw pointers in these template projects. Oh well, let's move on. Let's go to the CPP file for the third-person character. We need to include the header file for the Grind Effects component. Now, here in the constructor is where we'll create an instance of a Grind Effects component and assign it to the Grind Effects component member variable. Great. Now the character class owns a Grind Effects component. Let's go back to the header file for the Grind Effects component class. Alright, so what exactly does this component need? This component needs something called a Niagara component. So let's declare a pointer to a Niagara component. So the Niagara component has something called a Niagara system, and the Niagara system is a particle system that's used in Unreal Engine. Later on, we'll go over how to create a Niagara system that generates the spark particles. The Niagara component has a transform, so it has a location, rotation, and scale. We're going to attach Niagara components right below the character's feet, so the sparks generate at that location. This means we need two Niagara components, one for the character's left foot and one for the right foot. Let's declare one for the left foot and name it left foot grind sparks. Now let's declare one for the right foot and name it right foot grind sparks. Also, don't forget to forward declare the Niagara component class. Let's go back to the GrindFX component.cpp file. We need to include the header file for the Niagara component. There it is. Now, since we're using the Niagara system, we need to include the Niagara module. So open the build.cs file for our primary module. So in our case, it's the grindingtutorial.build.cs file. For this tutorial, the grinding tutorial module is our project's primary module, and we haven't made any other modules. We need to tell this build file that this module depends on the Niagara module. So let's add Niagara to the public dependencies list. Let's compile this just to make sure everything is working fine. Alright, we have a successful compile. Let's head back to the grindfx component.cpp file. Here in the constructor is where we'll create our Niagara components. One for the left foot variable and one for the right foot variable. Okay, so an actor component has a Boolean property called bAutoActivate, which indicates if we want the component to activate immediately after it's created. We don't want our Niagara components to activate automatically, because we only want them to activate when the character is grinding. We only want the spark particles to activate when the character is grinding. So what we need to do is set bAutoActivate to false for our left foot and our right foot Niagara components. Okay, cool. Let's compile and run this. Let's open the blueprint for our third-person character. Let's click on the character's GrindFX component. Here in the details panel is where we'll find the left foot GrindSparks Niagara component and the right foot GrindSparks Niagara component. Let's open this drop-down menu so we can see the component's properties. Here in this Niagara System Asset property is where we'll assign the Niagara system that will generate the spark particles. And we'll do the same for the right foot GrindSparks. So what we're going to do next is create the Niagara system. Let's close this blueprint and go to the grinding folder. Here is where we'll put our grinding Niagara system. So right click, go to FX, and click Niagara system. For our Niagara system's base, we're going to choose the fountain Niagara emitter. So search for fountain, and let's select the fountain Niagara emitter. Click create. I'm going to rename it as ns_grindsparks. Let's open it. Before we get started, I'm going to change some of the preview settings so we can clearly see what we're working with. Alright, so here is our GrindSpark's Niagara system. Every Niagara system needs at least one Niagara emitter, and here we'll be using this fountain emitter. This emitter spawns a bunch of particles that follow a fountain-like path or a cone path. This will be great as a starting point for our GrindSparks. So this fountain emitter has a bunch of different properties that we'll want to modify. First, let's delete this module called Shape Location. The reason why we should delete this is because we want the particles to emit from a single point. Right now, the particles are emitting from a sphere shape at the bottom, so it looks like a cone with the sphere hole at the bottom. I want the bottom to look like a perfect cone where the particles emit from a single point. You can check and uncheck this box to see the difference. I'm going to delete it. Next, we're going to modify this module called Initialize Particle. Let's click on that. So this Initialize Particle module has many different attributes and settings that will affect the particle's behavior and appearance. We'll start off with these two properties here, the lifetime min and lifetime max property. This will allow us to set the particle's lifetime, so how long each individual particle will be alive for. Now we're going to use a random lifetime, and it's already set to have a random lifetime between 1.4 and 1.75 seconds. I want the lifetime to be really quick, so I'm going to set it between 0.122 and 0.5 seconds. Feel free to play around with these settings however you want. You might end up with something that looks way better than what I came up with. Alright, the next thing we're going to do is set the color of these particles. Open up this drop-down menu, and here is where we'll set the RGBA values. I'm going to use these values here. Now our particles have a fiery spark color, which looks pretty cool. If you want, you can also change the color mode to random hue saturation value to add some randomness to the color. I won't be doing this, but feel free to try that out and tweak some of the values. Next, we're going to scroll down to these properties that alter the size of each particle. So right now, each particle is going to have a random size between 6 and 12 centimeters. I'm going to decrease the size to a minimum value of 1 and a maximum value of 2. I want them to be really small. Later on, we'll be stretching out these particles in the direction of their velocity. Now we're going to move on to the module called Add Velocity, so click on that. So here in the code settings is where we'll modify the code's orientation. We don't want these particles to emit in the upwards direction. We need to rotate this so the particles are moving in the horizontal direction. So for the cone axis, I'm going to set its x component to -1, and everything else will be 0. This way, the particles are going to shoot in the backwards direction. So if the positive x-axis direction is the forwards direction, we need to set x to -1 so it moves in the backwards direction. I'm also going to modify this cone angle property. I'm going to set it to around 8 or 9. So if we look at this from a side view, increasing this value will increase the angle of the cone that the particles follow. I think this angle looks good, but you can of course change it to whatever you prefer. Alright, the next thing we need to do is delete this module called Gravity Force. The reason why we're doing this is because I don't want gravity to be applied to these particles. You see how the particles start to fall downwards at the end here? I don't like how that looks. I want the particles to move in a straight path. Okay, so the final thing we're going to do is stretch out these particles, and we want these particles to stretch out in the direction of their velocity. Click on this sprite renderer module. Now I want these sprites to be aligned to the velocity, so later we'll scale it with the velocity. So here in the alignment setting, I'm going to set it to velocity aligned. Next, we're going to add a new module to this particle update group called Scale Sprite by Speed. So this min and max scale factor will determine how much the sprite is scaled by its velocity. I want the particles to be stretched in the horizontal direction by the velocity, so for the y component of the max scale factor, I'm going to set it to 20. Now you can see it's stretching out in the horizontal direction. I don't want it to scale in the vertical direction, so I'm going to set the x components to 1. To be honest, I don't know why scaling it along the y-axis scales it in the horizontal direction, and why the x-axis is the vertical direction. I thought it would do the opposite, but it probably has to do with the way we oriented it. Regardless, we got it working the way we want it to. Alright, and that's pretty much it for our GrindSparks Niagara system. What we need to do now is assign this to our left and right foot Niagara components. So let's open our third-person character blueprint. Click on the GrindEffects component and open the properties for the left foot GrindSparks. And here in this Niagara category is where we'll find the Niagara system asset for this Niagara component. Set it to the GrindSparks system we just made. We're going to do the same thing for the right foot GrindSparks. Alright, let's compile, save, and close this. Before we continue, let's add an instance of our GrindSparks Niagara system into our level and see how it looks. So let's drag and drop this into our level. Okay, I think this looks pretty cool. I just wanted to demonstrate how it looks, so I'm going to delete it now. Okay, so now that we have our GrindSparks, the next thing we need to do is figure out how we're going to attach these GrindSparks to the character's feet. We're going to accomplish this by taking advantage of something called a skeletal mesh socket. Skeletal mesh sockets are sockets that you can place onto your skeletal mesh. Obviously. You can attach components onto these sockets. For example, a socket on your character's right hand to attach a weapon to. What we're going to do is add sockets beneath the character's feet. One for the left foot and one for the right foot. And our code is where we'll attach our left and right foot GrindSparks onto these sockets. So let's get started. Open the header file for our GrindEffects component class. The first thing we're going to do is declare a member variable that will be a pointer to the character that owns this GrindEffects component. We'll need access to the character owner in order to get their skeletal mesh component. Next, let's go to the CPP file. Let's include the header file for the character class. Let's scroll to the begin play function, and here is where we'll set the character owner member variable. It's going to be set to the owner, so let's call getOwner. But we also need to cast this to the character type. Instead of using the cast function, we should use the castChecked function. This function has an assertion that will crash the game if the cast is unsuccessful. The reason why we should use castChecked is because the owner of this component needs to be a character. This component shouldn't be owned by any other class that isn't a character. Alright, the next thing we're going to do is attach the left foot GrindSparks and the right foot GrindSparks to the character owner's skeletal mesh. Let's start with the left foot. So we're going to check if the Niagara system asset is valid. If it's not valid, that means the Niagara system hasn't been assigned and we shouldn't continue. So if it's valid, we're going to attach the component to the character skeletal mesh. So call attach to component on left foot GrindSparks. For the first parameter, it needs the scene component that we're attaching this to. We need to pass in the character skeletal mesh component, so let's call getMesh on character owner. The next parameter needs an attachment transform rule, and here we'll be using snap to target including scale. The reason why we chose this is because we'll be attaching this component onto a socket that is placed on the skeletal mesh. We want this component's transform to match the socket's transform. So we want this component to have the same location, rotation, and scale as the socket. This transform rule allows us to do that. The next parameter needs the name of the socket that we're attaching this component to. Now, this is totally up to us, so let's actually define some member variables that store the socket names. Let's go to the header file. So it's going to be an f name called left foot grind socket name. We'll also make another one for the right foot. Now for the uProperty specifiers, I'm going to make it visible anywhere, not editable anywhere. The reason why is because I want to set these names in the class's constructor, and any skeletal mesh that wants to use this component needs to have sockets whose names match these names. I kind of want to restrict the socket naming, so designers are on the same page about what the name should be, instead of being able to freely edit these names in blueprints. For example, if one designer updates these names in blueprints, but it turns out that there were several different skeletal meshes that use the old names, that can lead to issues. I hope that makes sense. Let's head to the CPP file. Here in the constructor is where we'll assign the names. The socket name for the left foot is going to be called foot_L_grind socket. This is the naming convention for socket names. The foot_L prefix means left foot. Now let's assign the socket name for the right foot. Foot_R means right foot. Now let's pass these into the attachment function calls. I'm going to copy and paste this and modify it for the right foot. Alright, so we're done running the code that attaches these components to the character's feet. I want to improve on this and refactor this code into a function. So let's cut this, and we'll be putting this code into a function called attach sparks to mesh. Let's define this function. One more thing I want to do is check if the character owner and the character owner's skeletal mesh is valid. So I'm going to add an assertion here. So the game will crash if these are null, which means something went wrong with our code. Okay, before we continue, I just want to recap what we just did. So the purpose of this function is to attach the left foot grind sparks and the right foot grind sparks to the character's skeletal mesh. First, we check if the character owner and their skeletal mesh are valid. If they are, we'll first check if the Niagara system asset was assigned for the left foot grind sparks, so that ns_grind Niagara system we made. If it was, we're going to call a function on the left foot grind sparks called attach to component, which will attach this to another scene component. We want to attach this to the character's skeletal mesh, so here we pass in the character's skeletal mesh. We're going to use this attachment transform rule, which means it's going to use the parent's transform, and we need to attach this component to a socket on the mesh. So this left foot grind spark socket name variable stores the name of the socket that will be placed under the character's left feet. So we pass that variable in so it successfully attaches to the socket with that specific name. And here, we're just doing it over again for the right foot associated variables. Alright, I hope all that made sense. Oh, and before we compile and run this, I'm going to activate the components and begin play, just so we can see it working. Later on, we'll remove this because they should be activated only when the character starts grinding. Let's compile and run this. Okay, so what we're going to do next is create the sockets on the character's skeletal mesh. So let's look for the character's skeletal mesh. So here's the skeletal mesh. I'm going to look for the bone that's associated with the character's left foot. It's going to be foot_L. You can see here that this bone already has a socket called foot_L_socket, but I'm not going to use it. I'm going to show you how to make a new socket because it's really simple. So on the foot_L bone, right click and choose add socket. Now we're going to rename the socket to the name that we defined in our GrindEffects component. It has to match exactly. And I already forgot what the name is, so let's open the third-person character blueprint. Click on the GrindEffects component. Now here in the GrindEffects category is where we'll find the socket names. So for the left foot, it's called foot_L_grind socket. Let's copy that name and paste that name in for our new socket. Now let's repeat this process for the right foot. So the bone we need to look for is called foot_R. And let's just repeat the things we did for the left foot. Now we need to adjust these sockets. Let's work on the right foot first since we're already here. We need to rotate them and move them below the feet. So we want the red axis to point forward, the green axis to point to the right, and the blue axis to point upwards. So let's snap it to 90-degree rotations. Alright, that orientation looks good. Now let's translate it down below the character's foot. Awesome. Now let's do the same for the left foot. Alright, we can finally test this out. Awesome. As you can see, the spark effects are activating right below the character's feet. Great job, guys. The next thing we need to do is figure out how to activate these effects only when the character is grinding, and deactivate them once the character stops grinding. So our third-person character needs a way to be notified when the character begins or stops grinding. That way, the character can call the activation and the deactivation functions on the GrindEffects component when it's time to do so. The way we're going to do this is by taking advantage of something called delegates. If you don't know what a delegate is, think of it as an event. Different objects can subscribe to a delegate in order to be notified when a certain event occurs. We're going to be declaring our own delegates for events specific to grinding. We'll declare a delegate called onGrindBegin, which will notify its subscribers when the character starts grinding. We'll also declare a delegate called onGrindEnd, which will notify its subscribers when the character stops grinding. We're going to declare these delegates in our custom character movement component class, and our third-person character will subscribe to these delegates so the grind effects will be used at the right time. There's a great article written by Unreal Garden that teaches you all about delegates. I'll leave a link to it in the description. Just a side note, this is an example of a software design pattern called the observer pattern. When a certain event on an object happens, that object can notify other objects or observers that are subscribed to this event. That is the basis of the observer pattern. Delegates implement this pattern. So let's close our project and open the header file for our custom character movement component. What we need to do now is declare our delegates. So here, right above the class definition, is where we'll declare our delegates. So in order to declare a delegate, we need to use this function macro that starts with declare_delegate. Now, our delegates can have parameters, which allow us to pass in information to functions that are bound to the delegate. In order to add parameters to a delegate, we can use the function macro that's associated with the number of parameters we need. For example, if it needs one parameter, add one param. If you need two, add two params. For our delegates, we won't need any parameters, so this will be the function macro we'll use. This is also a non-dynamic single delegate. There's a lot to delegates that I won't be able to cover in this tutorial. If you want to learn more about them, please check out Unreal Garden's article on delegates. You'll find the link in the description. Okay, so for the first parameter, it needs the name for our delegate type. Our first delegate is going to be called onGrindBegin, so let's pass that in. Unreal's naming convention for delegate types is to have their name begin with the capital letter F, so let's add that. They also end with the word signature. That's pretty much it for the delegate declaration. I'm going to copy and paste this and rename this to onGrindEnd. So this delegate will notify subscribers when the character starts grinding, and this one will be for when the character stops grinding. What we need to do next is add these delegates to our custom character movement component class as public member variables. This way, our third-person character class can access and subscribe to them. So here, we'll create instances of our delegates. This will be called onGrindBegin. This will be called onGrindEnd. Now let's go to the CPP file and look for the code where grinding begins and where grinding ends. Let's scroll down to the onMovementUpdated function. Remember, this function is called whenever a character's movement has been updated, obviously. So here, we can check if the character has fully transitioned onto the grinding platform. Internally, this class already considers the character to be in a grinding state as soon as they enter the grinding movement mode. However, from an external perspective, grinding doesn't officially begin until the character has fully transitioned onto the grinding platform and actually starts grinding. This scope represents that moment when the character fully transitioned onto the platform and started grinding. This is the point where the delegate should notify all of its subscribers that grinding has begun. In order to notify its subscribers, we need to call the executeIfBound function. So any functions that are bound to this delegate will be executed. Alright, now we need to find where the character stopped grinding. That happens here in the onMovementModeChanged function, specifically in this scope, because this scope executes when the previous movement mode is the grinding movement mode. So here is where we'll get the onGrindEnd delegate and notify its subscribers that grinding has completed. Okay, great. We've completed writing the code that notifies when the grinding events occur. The next thing we need to do is get our third-person character to subscribe to these delegates. That way, the character can activate or deactivate the grind effects when one of the corresponding grind events occur. Let's navigate to the header file for our third-person character class. What we're going to do is override a function called postInitializeComponents, and I'll explain what this function does and why we're using it. So here's the function signature. So this function is called immediately after every single actor component has been registered and initialized. Every single actor component that this object owns, so our third-person character. This function is great if you need to do some setup or initialization code right after the actor components are ready. It's after the constructor, but before begin play is executed. This is a very common place to subscribe to delegates. You want to reduce as much code in begin play as you can, because if a lot of things are happening in begin play, then you'll cause a pause right when your game starts. So instead of subscribing to delegates in begin play, do it in post-initialize components. The constructor is too early. With that being said, let's subscribe to onGrindBegin and onGrindEnd. Let's call the parent version of this function. Now let's get our custom character movement component by calling getCharacterMovement. We need to cast the return character movement component to a custom character movement component. On the custom character movement component, let's get the onGrindBegin property. Before we move forward, I think it would be a good idea to cache this custom character movement component into its own member variable. Let's go to the header file and forward declare the custom character movement component class. Now we'll declare a pointer to a custom character movement component. It's going to be called custom character movement. I'm also going to implement a getter function for this variable. It's going to be called getCustomCharacterMovement. Let's go back to the CPP file. Now here in the constructor is where we'll set that variable. We can just copy and paste this code. Now we have a pointer to our custom character movement component instead of needing to cast it every time we need it. Alright, let's add our getter function here. Now here is where we're going to subscribe to onGrindBegin. We do that by calling the bindUObject function, which allows us to bind a member function. The first parameter needs the object that owns the member function that we're binding. Now, I'm not going to pass in the this pointer. I'm going to pass in our grindEffects component. So when we're notified that the character started grinding, I want a function on the grindEffects component to be called that will activate the effects. Let's actually go to our grindEffects component class and define the functions that activate and deactivate the effects. So here in the header file, I'm going to declare a public function called activateGrindEffects. We're also going to declare a function called deactivateGrindEffects. Let's create the definitions for these functions. Let's start with the activation code. So I'm first going to check if the Niagara system asset has been assigned for the left foot Niagara component. If it was, let's call a function on it called activateSystem. Now we're going to do the same for the right foot Niagara component. Let's copy, paste, and rename these for the right foot. Alright, now let's scroll to the deactivate grind effects function. First, I'm going to check if left foot grind sparks is active. If it is, we'll deactivate it. We're going to do the same for the right foot, so copy and paste it. Rename this. Okay, so now we have our activation and deactivation functions. Let's go back to our third-person character CPP file and let's bind those functions. So for the second parameter here, we're going to pass in the memory address of the activation function we just made. Alright, so when the character starts grinding, this onGrindBegin delegate will fire off and call this activate grind effects function that is on our grind effects component. Let's do the same for the onGrindEnd delegate. So let's copy and paste this. Rename this to onGrindEnd. So when this delegate fires off, I want it to call the deactivate grind effects function. So let's rename this to deactivate grind effects. Alright, I hope everything we've done so far makes sense. Please let me know if you need help on anything. Oh, and I almost forgot. Let's go to the grindeffects.cpp file and remove this code here in the begin play function. This code was just for testing. Alright, let's compile and test this out. Awesome. The grind effects activate when we start grinding, and they deactivate when we stop grinding. Awesome job, guys. Alright, there's one last thing we need to implement, and that is the grinding sound effects. After that, we're completely done with this tutorial. So, in the grinding assets folder that I provided in the description, there should be a WAV file called grinding. What we're going to do now is create a meta sound source that will play the WAV file. So let's go to our grinding folder, right click, choose audio, and choose meta sound source. Let's rename it to ms_grinding. Let's open it. Alright, so here it is. What we're going to do first is add this mono wave player node. Now we're going to plug this input pin into this play pin. Now for this wave asset option here, we're going to set it to our grinding wave file. We're also going to check this loop option here, because we want the sound to loop for as long as our character is grinding. We need to plug this onFinish pin to this output node. We also need to plug this out mono pin into this. Alright, cool. Something else we need to add to this meta sound source is something called attenuation. Attenuation allows a 2D sound to become 3D, so it will allow the sound to adapt to our location in the level. So the farther we move away from the sound's location, the quieter the sound will become. So it gives that 3D effect. So in order to add attenuation, we need to create a sound attenuation asset. Let's go back to the grinding folder. Right click, go to audio, and choose sound attenuation. Let's rename this to ATT_grinding, so attenuation grinding. Let's open it. I'm not going to spend too much time on attenuation, so most of the default settings are good, but I'm going to set this inner radius setting to 300. So once you get 300 centimeters away from the sound source, the volume will start decreasing the farther you are away from it. I'm also going to change this fall off distance setting to 1200. So once you're 1200 centimeters away from the sound source, you won't hear any sound. Play around with these settings and see what you like best. Let's save and close this. Let's open back up our grinding meta sound source. Now we need to assign our attenuation settings, so click on this source button, scroll down to the attenuation settings, and assign it to the ATT grinding that we just made. The last thing we need to do for this meta sound source is to change the virtualization mode. We need to switch this from restart to play when silent. If we left it as restart, we won't be able to hear the sound again once we exit the fall-off distance. This way, the sound continues to play even when we're far away from it, so it knows to start playing again once we're close enough to it. Let's play this. Okay, it sounds fine, but we don't really know how it sounds in 3D. So what we're going to do is drag and drop this meta sound source into our level, just to test it out. You can see how it has a sphere outline. Once we leave that sphere, the volume will start to fall off. So let's play this. Right now it's at full volume because I'm inside the sphere, but once I leave the sphere, the volume will decrease. Let's get back into it, and now it's increasing. Alright, great. The next thing we need to do is figure out how we're going to attach this sound to our third-person character. We want the sound to follow the third-person character wherever they go, and only be played when they're grinding. We're going to accomplish this with something called an audio component. Let's first delete this MS grinding instance. This was only used for testing purposes. Now let's close this and open the header file for our grind effects component. This class is going to need something called an audio component, so let's for declare the audio component class. Let's also create a member variable that will be a pointer to an audio component. We're going to call it grind SFX. So what an audio component allows us to do is attach audio to another component. We'll be attaching this component to our character's mesh. So let's open the CPP file, include the header file for the audio component class. Here in the constructor is where we'll create an instance of an audio component and assign it to our grind SFX pointer. We also want to set the BAutoActivate property to false. We don't want audio to immediately start playing. Let's compile and run this so we can assign our grinding meta sound source to this audio component. Let's open the third-person character blueprint and select the grind effects component. Here in the grind effects category, we'll find the grind SFX property, which points to our audio component. Let's open the sound category, and here we'll set this sound property to our ms_grinding meta sound source. Alright, cool. We're not done with our code, so let's close this and head back to the CPP file. Our next step is to attach the audio component to the character's mesh. Let's scroll down to the attach sparks to mesh function. What I want to do here is modify this function. Instead of having this function be responsible for only attaching the sparks to the mesh, I want this function to be responsible for attaching all of the necessary components to the mesh. This includes the sparks and the audio component. So what we should do is rename this to attach to mesh. Let's also head to the header file and rename the function's declaration. Oh, and don't forget to rename this function call in begin play. Alright, so in this function is where we'll attach the audio component. First, we need to check if the sound property has been assigned already. We can do this by calling getSound. If it was, then we'll attach this component to the character's mesh. For the attachment transform rules, this time we're going to use snap to target, not including scale. There's no reason to modify the scale of the audio component. The only important transform property is the component's location. Now that we've attached the audio component, now we need to write the code that will play the sound at the appropriate time. So let's scroll to the activate grind effects function and play the audio. So first, check if the sound property was assigned. If it was, we'll call the play function on the audio component. Let's scroll to the deactivate grind effects function, and here is where we'll stop the audio. We do this by calling the stop function. Let's compile and test this out. As you can see, our grinding sound plays when we start grinding, and the audio file will loop for as long as the character is grinding. When we stop grinding, the audio will stop as well. Let's check if the attenuation settings are working properly. I'm going to move this third-person character right above the edge so it falls and starts grinding when we play the game. So the sound is playing for the character. Let's try moving away from the character. Now the volume is decreasing, which is exactly what we want. Now let's move towards the character, and you can hear the volume increasing. Awesome, everything is working properly. And that's pretty much everything for this tutorial. It took a lot to get here, but we finally completed developing this grinding system. This was a lot of work, but you guys did an awesome job getting through all of this. Thank you so much for sticking around to the end of this tutorial. I hope this was helpful for the game that you're working on. Please leave a comment if you have any questions, feedback, or want to say absolutely anything. I'd also love to see the game that you're developing, so feel free to show me whatever you're working on. Also, don't hesitate to connect with me either through LinkedIn or anywhere. I'll leave my contact information in the description. Thank you so much for letting me be a part of your game dev journey, and take care. Bye-bye.